Hello, Sean. Good to see you. Yeah, so for the most recent people to join, we'll wait a few extra minutes just to make sure everyone who intends to join has time to get into the webinar. So when the attendee counter stops growing rapidly, I will get started. Yes, Nick, the audience is muted by default. I think we can technically allow audience members to speak, but there will be a Q&A tool as well. So it should be sort of the tool. There should be tools to get your questions through. Do you have a question, Pedro? You're raising your hand. Yeah, all right. So I think we can get started. So welcome back, everyone, to the Understanding Latency webinar series. My name is Björn Everteigen, and I am head of research at Domus, and I will be guiding you through today's session, whether it's morning, afternoon, or evening for you. So the anticipation for this event has been building for quite a while, and we're thrilled to finally bring it to you. We have an outstanding roster of speakers, and it's truly astonishing to see the level of enthusiasm and interest that the event has attracted. The previous Understanding Latency event was in March of this year, and we were very pleased with the attendance and reception of that event. And we feel like the focus on latency really struck a chord with the industry. And that was also evident at this year's Network X event, where we saw that more vendors and operators are now talking about improved latency as a selling point. And that is why we decided to host another event already, which is to keep accelerating the momentum and hopefully make the low latency internet a reality as soon as possible. So First, some practical sort of details. This will be a knowledge sharing event, and the point is to share experience, insights, best practices related to measuring and improving latency. And so the event is about highlighting a problem space and the solutions to those problems that all of us have a shared interest in tackling in the best way possible. So that's just to say we are not it's not a sort of a sales event or a marketing event. It's a technical event with focus on data, problems, and solutions that we all share. So we will have a series of talks every day. Each talk will be 15 minutes, and after each talk, we'll do a Q&A. So we'll sort of adapt the length of time that we have for Q&A based on how much time we have between talks, basically. So we invite everyone to ask questions. To ask a question, please use the built-in Q&A tool in Zoom. So there is, you should see at either the bottom or the top of your screen, you should see a Q&A symbol. And I mean, feel free to ask questions in the chat as well, but we might miss those. So if you add them to the Q&A tool, all the presenters get a list of the questions, and so it's much easier to keep track of them and make sure that we don't forget any. So, and also please note that the webinar is being recorded, and so questions and answers, for that matter, will be part of the published recording, and that will be put up on YouTube, and we will send out an email to everyone who's registered as soon as they are ready. And we will also attempt to make all of the slides available in a link in that same email. So hopefully finding the presentations and the talks and stuff like that should be easy once the webinar is done. All right, I think that's all of the can you not hear me, Gavin? Can other people hear me? Okay, good. Then it's at your end, Gavin. Sorry about that. Okay. So before we get to sort of the quote unquote real speakers, please allow me to present a short introduction to the topic of latency. I have titled my presentation Network Latency 101. And I will bring that up as soon as I can. Let's see. There we go. That should be working now, hopefully. Yep, there we go. Yes, the question, the meeting is being recorded, and so it will be uploaded to YouTube. And if you're registered for the webinar, you will get an email with a link to the YouTube as soon as that's ready. Okay, latency 101. Let's go. So the agenda for this one is why latency is sort of singled out as a metric that is, well, why is latency so important? There are many metrics that we could be focusing on. Why do we care so much about latency? And then I'm going to do sort of a brief high-level overview introduction to what causes latency. Why do we have latency in our networks at all? And so it really begins with this observation that users consume applications, not networks. And so our job as network operators and vendors and people who build networks is really to make sure that all of the applications that people use that rely on the network that all of these applications work as well as they possibly can. That is the whole point of building networks in the first place. And to accomplish that goal, more bandwidth is certainly good. And that is sort of, so bandwidth or network capacity, megabits per second, throughput, it has many names, but bandwidth or capacity is good. It is necessary. And it's sort of the metric that has been what the industry has been focusing on in terms of what the industry is marketing, what we're aiming to build more of, and stuff like that for a long time. And bandwidth, it measures time to last bit, if you like, for very large transfers. So if you have a 50 gigabyte file, a game update or something like that you need to download, how quickly you can do that is pretty much a function of the capacity of your link. And that's, I mean, being able to download large things quickly is a good thing for sure, but it's not necessarily where most people are having problems with their network connection. So I will argue that latency has a much bigger impact on quality of experience. But what is latency? And I like to think of it as sort of the time to the first bit, if you like, for every single transfer, everything you do on the internet. So be that sort of getting the weather forecast or reading the news or web, like just general web browsing, video conferencing, gaming, AR, VR, anything that you use the internet for, latency measures the time to get sort of a connection set up or to fetch the next HTTP segment that you need for a video to stream smoothly. All of that is related in some way to the latency of your connection. And this is some data to back that statement up. So on the top here, we are looking at how the web page load time for just some website, how that scales with the capacity or the bandwidth of your link. And as you might notice, these numbers, these throughput numbers are very small compared to what a lot of ISPs are offering today. So on the left side, we have 1 megabit per second, and then on the right side, we have 10 megabits per second. And then the y-axis is the page load time. And as we can see, around 5 megabits per second somewhere, the page load time doesn't meaningfully decrease anymore as you increase the bandwidth or the capacity of the link. But on the bottom graph, the orange columns, we can see that as latency decreases, the page load time improves a lot, and it's almost linear relationship. And so this is just one example of how improving capacity doesn't necessarily improve the outcomes that customers or consumers care about for their networks, whereas improving the latency really does. Okay, so then what causes this latency? And I have split it into a few things. So on the top level, I split it into application layer, servers, and end hosts, and then network delays. And I just wanted to mention that application layer, the application layer and the operating system and the server side, and there are a lot of pieces that are not necessarily thought of as part of the network that also add latency. So it's important not to forget that those are also part of the end-to-end equation here. But then there is the network delays. And honestly, network delays are fairly often a very significant part of the end-to-end delay. And I will focus on network delays in this talk. And network delays can be further split into three categories here. First one is distance, and I will show that for the best case, we are pretty close to the theoretical optimum when it comes to how much latency the distance variable adds, if you like. And then there is serialization delay, and this used to matter a lot. This was many years ago, this was or maybe one of the most important things was serialization delay. I will show that at 100 megabits per second or more, serialization delay is almost completely insignificant, and we can ignore that part of the end-to-end for most purposes. And then there is queuing. And I've included in this one also waiting for media access. And in my opinion, that is sort of the big one. So let's jump into each of these in turn. So distance, I was at the IETF meeting in San Francisco this summer. And when I was there, I measured the delay to a server in Frankfurt. And I got a minimum round trip delay of 148 milliseconds. So is that good? Let's find out. This is the distance from San Francisco to Frankfurt if we just do like a shortest path along the surface of the Earth. So we're not going through the Earth here. The distance is about 9,000 kilometers. And so the round trip is slightly more than 18,000 kilometers. Now at the speed of light in a vacuum, which is about 300 kilometers per millisecond, that's 61 milliseconds. But speed of light in fiber and in copper is roughly 2/3 of that. So we have to work with 200 kilometers per millisecond instead. And then we end up with about 91 or 92 milliseconds round trip. But that is going in a straight line along one of the great circles. And so fiber doesn't take that path. So probably the signal has gone across the US somehow by land to area around New York, across the sea to Dublin somewhere, and then over to the continent. That's a longer line. But even this is 91 or 92 milliseconds, and then I measured 148. So we're within like 50, 60 milliseconds of the theoretical perfection here. So that is just to say that the industry has done an amazing job at optimizing these things so that we are very close, within a factor of 2 of like light speed delays, which is, in my opinion, quite amazing. But it also shows that optimizing for distance is sort of, that is not where our gains will come from, if you like. Then we'll look at serialization delay. And these two bars are representative of two different numbers. The first one, the big blue bar here, is the time it takes to send a 1500 byte packet at 64 kilobits per second. And it's almost 0.2 of a second, and we can only send less than 6 packets a second at this rate, because each packet takes so long to actually serialize and send over the wire. Whereas at 100 megabits per second, sending that same 1500 byte packet takes 0.12 milliseconds. So we can send more than 8,000 packets a second at 100 megabits per second. And so the conclusion here is that more bandwidth, adding or improving the link rate the capacity of the link used to result in very much lower latency, simply because we could reduce this. So if you moved from a 64 kilobit to a 256 kilobit per second line, you could slice this in it to 1/5, right? Whereas going from 100 megabits to a gigabit only shaves off about 0.1 of a millisecond. And in the sort of great scheme of things on the internet, 0.1 of a millisecond, it's almost nothing. So improving, and this is just to sort of put some perspective on it, because some people will point out that improving capacity reduces delays because each packet can go faster. And that is technically true. It's just that the scale of that effect is so small that when we were talking about how to make the internet faster or more responsive, that is not where we should put in our efforts, basically. So that gets us to the final thing, which is queuing. And what causes queuing? And in my opinion, it's fairly simple. Queues form when resources are overloaded. And that can happen in two different ways. So imagine we have a system that has perfect balance between users arriving or sort of requests for resources and the servers that can service those requests. So every time a customer arrives, another one leaves, and it's perfect balance. Now, there are two ways in which that system can be knocked out of balance. And those two ways are either more customers can suddenly arrive so that there are too many customers arriving, and now a queue is forming because the customers can't be serviced quickly enough. The other thing that can happen is that one of the servers can leave or shut down or no longer be able to service clients. And that will also cause the same effect, where now queues are growing because that same volume of demand that used to be like just the right amount is now too much. And that's important because in the internet, we very often internet engineering has been focusing on how do we account, or how do we deal with sudden bursts of too much demand caused by too much arriving traffic. But we also have to take into account what happens when the supply side suddenly can't supply what we used to get, which is a common problem with wireless, for instance. And then a final point is that resources can be overloaded on many timescales. So if we're looking at very short timescales, then we're looking at some, like, for instance, what we call jitter or latency spikes. And on the sort of minutes or longer, we're looking at sort of more things that can be planned for, basically. So if we're looking at the capacity balance, or the sort of supply and demand balance on a scale of hours or weeks or months, then we can do things like add more capacity, add more servers, build out more fiber, things like that. Whereas on the millisecond to second scale, there is no time to sort of make more resources appear. And so there has to be rules built into the system to deal with those temporary overload events, basically. And I just wanted to split those two different scenarios because they have different consequences for the users, and that they have very different consequences in terms of how we can deal with the problems. So final point is, or final slide is this example where I measured, I took a nuclear speed test on a 5G network here in Norway. And this is just to show that this queuing problem is real. So we have pretty decent numbers in terms of download and upload. But the numbers that we need to focus on here is these the ping numbers, and the yellow ping, which is the idle ping, is pretty good, 18 milliseconds, not too bad. The download, uh, when a download is running, the ping grows to 367, which is not great. And the same with the upload, where it's 135. But this is just to show that this queuing problem or buffer bloat is a very real issue in the most modern, most hyped networks that we currently have. So with that, I conclude my talk, and we'll be happy to answer questions. I haven't been able to follow the questions while I've been talking, so let me just look at the list. So we have, what data rate was used for the page load time versus latency? That's a good question. I don't know, actually. So I assume you're talking about this slide. Well, the data rate for this one is 1 megabit to 10 megabit. For this one, I assume they have kept the 10 meg, or the data rate is not the bottleneck for this, right? So they, I would assume it's 10 or even higher, because this graph will just approach some plateau, and so it doesn't really matter which rate you use as long as you're on the plateau. Okay. Any more questions? Or okay, then I will stop sharing. And you can get ready, Sean. So our next speaker is Sean Dubois. He will be talking about WebRTC. He is the creator of Pion WebRTC, which is a Go client for WebRTC, and author of WebRTC for the Curious, which is an introduction to WebRTC, a book. He's currently the CTO of LiveKit, which is an open source alternative to Agora or Twilio built on Pion. So with that, Sean, please feel free to take the stage.
Great. Thank you so much for having me. Let me make sure I have the questions open. I'm going to wait for like people to like spam and say, I can't hear you. Okay.
Cool.
So
We
yeah,
can hear you. I can confirm.
okay. Nice. Okay. Cool. So, first thing I want to say is thank you. Like, so Pi is an open source project and lots of people have contributed to it. So I get this opportunity to get up and talk about the things that have been built or the things that, other people have explained to me. And I just want to say thank you. Like, here's everyone that's been involved. And there's been a lot more since I've pulled this list. It's been about 6 months. So yeah, as I go through this talk, like I don't want to take credit for all these things that I didn't figure out most of the stuff on my own. Most people explain it to me. So what this talk is I'm not like a full-time real-time networking programmer. Like I spend a lot of time like plugging protocols together and like implementing specs and stuff like that. Like my time worrying about latency and congestion control and stuff like that is really a minority of what I'm interested in. But I do see a lot of people struggle with understanding like how does WebRTC work and like how does the bandwidth estimation work and how do we deal with errors and stuff like that. And so this is talks kind of the arc of like my debugging and implementing and the things that I went through. So if you're already familiar with the stuff, you'll probably find this talk kind of frustrating because you've already done this and you're like, oh, and it'll talk through like all the mistakes I made. But if you haven't done this stuff, I hope that this will like put some light on the blind spots. So if you're not familiar with WebRTC at all, the parts that are going to matter today or what we're going to talk about is we chunk up these video frames. You know, you have like a very large video. Imagine you have like a very large video frame that's way bigger than an MTU. So you can't like put, 500 kilobits inside a UDP packet. And so this protocol RTP that's defined at the IETF defines how to chunk up things and send it over. And it needs to be sub-second, minimal buffering. And here's kind of like the story of um, Pion like pre-bandwidth estimation. So this is I went and I built Pion because I wanted to solve a particular problem. I wanted to make WebRTC. I wanted to make it easier to build things with WebRTC for people that had like custom needs. Like I didn't want you weren't putting up a server because you were building conferencing. You were doing something unique that didn't fit in with existing software. So the first thing I went and did is what's nice about WebRTC is I can go and I can look at all the specs. So the actual acronyms aren't important, but the point being is that I can go to the IETF and I can go through all these docs and I can be like, okay, I'm going to implement this, and I would copy the tests out of the bottom of it, and then like things would start to work. Uh, what I did run into at the very beginning was like bandwidth estimation isn't as clear. If I wanted to go and build this part, like I had no idea where to go. So there was a working group, RMCAT, and I went into it and there wasn't like a clear conclusion. And on top of that, like there wasn't like something that I could just copy tests out of run. It wasn't like implementing session description protocol where I copy the tests out of the bottom of the doc and I make sure they work. Or even with RTP, like pretty much all of these other specs I could go and look, but I found that bandwidth estimation is not something that I could just go and implement a spec and then like walk away from. Um, I think I'm not sure why it is that way, but for me, it seems like the space is still evolving. It's a more complicated problem. These other things like were implemented and we've been using them for 20 years, but as you see, like from the fact that we're having this webinar today, like this is still an evolving and people aren't sure. So one of the first things that people would come in is people would come into the Pion Slack or GitHub and they would start sharing like screenshots of broken video and say like things don't work. And at this point, my only conception of bandwidth estimation and latency and everything was like I knew that UDP drops packets. I'm like, if you send too much, packets will drop. I didn't think about it any more than that. Like I just cared about getting video into the browser. And so to talk about like what are these packets that are being dropped is here's a header for RTP packets. And so if you have video, like you're chunking up this video, and this is what you're putting it inside of. So the packet header has some identifying things like the SSRC says like, this is your video stream, this is your audio stream, and then you have like timestamps and other things. So this is how you chunk up the video itself. And next, you want to communicate back and forth about this video that's been chunked up. So if you're a sender, you want to say, hey, by the way, I've sent you 5,000 packets. I hope you got them all. And as a receiver, you can send back and say like, hey, I've got 4,922. Like I'm missing 88 packets. Like what do we do about that? And so you have the RTP protocol that actually contains the media and the RTCP protocol that contains the actual metadata. And this is how things go back and forth. And what I started with was someone told me about the receiver estimated max bit rate. So the de facto implementation for WebRTC is libWebRTC. It's in all the browsers, Google, hosted by Google, and it's available in Chrome, Firefox, Safari. Like maybe if they re-implement small parts of it, like libWebRTC is kind of like what everyone uses as like the de facto standard. And libWebRTC has an RTCP message called receiver estimated max bit rate. And all I'm doing is I'm like plucking out like if I'm sending video to Chrome, Chrome says, hey, you can send me 2 MB. And great, like that was very resolving. Someone opened a PR against Pion. We read those values out of it, and then we're all done. I'm like, great, all fixed. Like this whole conversation of bandwidth estimation is done. I can go back and solve other problems. But it only solves half the problem. Like, what if Chrome is sending the video? I don't know what number to pack into a receiver estimated max bit rate. Like, that's not something I understand. So what do I do here? I make libWebRTC do all the work again. So going back to that RTCP, we have these receiver reports, and it says like for an RTP packet, here's the number of packets that are lost, and here is the jitter, which is like as the packets come in, like are they coming in smoothly? So let's say like the first packet comes in and it takes 500 milliseconds to arrive, 500 milliseconds, and then the next one comes 600 milliseconds. That's jitter. So like the jitter is figuring out like are they arriving smoothly? And I got lucky. Like if I generate these receiver reports, which isn't a very challenging problem. Like you're just like you're you're collecting up all the RTP packets and you're generating the metadata. And if we generate those, Chrome adjusts their bit rate. So in bad networks, Chrome would send less, and then in good networks, Chrome would send more. Great, like I'm all done. And so the complaint comes in and someone says, hey, like, thanks for adding these receiver reports, but the slope at which the bitrate increases is slow. So these are on a little bit of different time scales, but you can see on the left was Pion with receiver estimated max bit rate, and the right was from Google Meet. And this is just like a GitHub issue I got. I still have no concept of how bandwidth estimation works, and I just understand receiver reports. That's all I've seen. And so I'm like, I have no idea why it's doing this. Like, I'm not sure what I'm doing differently. And someone says, okay, what actually you need to do is do transport wide congestion control. So this solves the same problem as those receiver reports, where when Chrome sends me packets, I'm sending back metadata about those packets arriving. And so, but this has even more information. So now I can say exactly when a packet arrived. And so a sender can say like, okay, like my packet one took this long to arrive, my packet two took this long to arrive. So I implement that, and all of a sudden the congestion control looks great. Everyone is happy. So as a little aside, it wasn't so much that the transport wide there wasn't something, it wasn't the transport wide congestion control reports that were doing something different. Um, in Chrome, their bandwidth estimator has a fast start, and the fast start is only enabled if you're using the transport wide congestion control. So like there's nothing about the feedback formats in particular that says one should start faster than the other. But my mindset at this time was I had no idea how bandwidth estimation works. It wasn't a problem I was worried about, and I was just responding to like user reports and things that don't work. And so to go through, like, didn't worry about bandwidth estimation at all. And what was happening now was that if Chrome was sending me video, I would send the transport wide congestion control ports, and everyone seemed to be happy. And if I was sending video, I would read those the REM values of the receiver estimated max bit rate, and I would just tell the user, okay, this is how much to send. And everyone seems pretty happy. Things are fine. But now it's time to go and implement my own bandwidth estimation. So this, if I like, let's say I wanted to send video from Pion to Pion, like I was getting more people that like wanted to do like headless clients into servers. They were putting it into robots and other stuff, and like there was no libWebRTC involved. So I have to go and figure this out. The first thing I did is I went around and I tried to ask like different WebRTC implementers that were available. There is a pretty good community that you can reach out to for like WebRTC servers. So Lorenzo is available. Like I asked him a bunch of questions. Varun, who's going to be up next later, is available, and I was able to ask him questions. Another great person is Sergio from Millicast. Like he was available to answer questions. And I kind of spent like 6 months kind of churning. I wasn't able to figure things out. Really, like one of the things I heard from everyone was that Google congestion control is the best thing to use, but you can't go look at the spec. Like it's incomplete, and it doesn't match up with what it does today. Like the implementation is the only thing that you can look at. There were other congestion control algorithms available, but kind of the anecdotes I always got was like, you should use Google congestion control. It's widely deployed and tested. Um, and I have no data to prove or disprove either way, which is better. Like this is just kind of the anecdotes I was given. The other thing I was told was maybe like you should go and look at BBR. It's more documented, it's widely implemented, and you can like tune it to do the things that you care about. But really, like the summary of the slide is I have no idea what I'm doing. Like I am a co-programmer that I'm trying to get video into the browser effectively, and across different things, and I'm trying to figure my way out, and this is the point that I'm at. But luckily that we had some experts that come filter in, so you'll see him later. But Dave Tate showed up in the Pion bug tracker, and a couple times he had reached out and said like, hey, you should be worried about buffer bloat, you should be worried about this, all these concepts I was not familiar with at all. And so this, as someone that doesn't understand latency and congestion control and all these things at the time, like this was a great resource. So I spent a lot of my time pouring through like the buffer boat mailing lists. Um, one of the users of Pion, Julius, and the WebRTC server Galeen, they had a lot of conversations on those mailing lists that I was able to read through. So that was super helpful. And then Dave introduced me to an Elnet, and we were able to get some funding to go and solve this. So now it's time to actually build a congestion controller, and someone came on to do that like full time. So Matisse was able to get money from an Elnet, and he went and worked on that. So if you want to know the actual guts and the implementation and stuff like that, a better person to go watch is the person that actually built it. So he did a talk, bandwidth estimation from scratch, and you can just look up for that on YouTube, or here's a direct URL when I share the slides. He goes in and discusses the interfaces and like the APIs and like all the feedback. I don't think that's too important, but the two concepts that I think really helped me out understand is that inside this congestion controller, there's this state machine, and it like will move between these different states of hold the current bit rate, increase the bit rate, or decrease the bit rate. And the reason you increase the bit rate or decrease the bit rate is because the link is being overused and it's underused. But like, why is it being overused or why is it being underused? And it comes down to like these two simple things, at least in the Pion implementation of Google Congestion Control, it breaks down in two places. It's either loss based. So if you're sending those RTP packets that we talked about earlier, and transport wide congestion control comes back and says like, hey, you've lost this percent of video, you need to decrease your bit rate. Or if you haven't lost any, you can increase your bit rate. On the other side, what transport wide congestion control gives us is the actual delay. So type on my slide there, but if the delay is increasing, you decrease the bit rate, or if the delay is decreasing, you increase the bit rate. So this is where that buffer bloat comes into. So if there is a hop along the way that is delaying your packets, it's probably because the machine is overloaded, the buffers are filling, and so you need to stop sending as much. And that's what we're able to infer from those transport wide congestion control reports. So go try it out. Like we have an implementation, bandwidth estimation from disk, where you can throw up some video files and go check out the code is in Pine Interceptor. So there's a couple things that we don't have, like fast start, and they've been ticketed, but we'll get to them eventually. But kind of what happened is we put out this GCC implementation, and a lot of the people that implement Pion ended up not using it because they were building servers. And so we didn't get that feedback, but continue to improve it. And that's where this next part is going. It's like this clients first servers. So we built this congestion control algorithm. And one of the things that I didn't appreciate or grok at the time was that these congestion control algorithms that were described earlier were more targeted at the clients because you could adjust the bit rate. And this is a core concept of WebRTC, which is simulcast. So if how WebRTC deals with these different quality layers is that each user actually uploads all their quality levels. So right now I'm probably uploading a low quality, a 480p, a 720p, and a 1080p, or a low, medium, high quality level. And the SFU, which is that server in the middle, is actually deciding what to forward. So the SFU says, okay, user C doesn't have a good network, so I'm going to send you everyone's low video feeds. But user B has a good network, so I'm going to start forwarding the high quality feeds. And this is like that core concept of most WebRTC server operators. It's not like RTMP and HLS where they're generating transcodes, they're running encoders. Like we're only doing network traffic just to save money and have lower latency. But the problem is if people were building things like that, they were running our Google Congestion Controller 3 times. So you have that publisher 1, that publisher 2, that publisher 3, and each of those colored boxes are like the different quality levels. So imagine that blue is the low, the green is the medium, the red is the high. I'm now running my congestion controller 3 times to forward video to the viewer. So that's like expensive. And these are the complaints I got back. Was first like generating of the probing packets. So with Google Congestion Controller, it talks about like, okay, raise your bit rate 10%, N%, but we can't do that with pre-encoded content. And that's actually not a hard problem. We generate probing packets. So you can like send packets twice, you can do forward error correction, other things like that. But the big complaint was that there's a lot of extra CPU and network overhead that doesn't need to happen. So you have like these competing congestion controllers, and they're all running their individual state machines. They're all generating their own probing traffic, and they're all like kind of competing with each other. And people that were building their own congestion controllers in-house were kind of trickling out this feedback that, hey, like what you have today doesn't work for servers. And so that's what Alexandria is solving right now. So now we have this like second generation, we have this congestion controller that's targeted at clients. And now we're going to work on defining an algorithm for a congestion controllers that are just targeted at servers. And this is actually like kind of a nugget of an idea that was kicked off by Varun. I was talking to him and he mentioned like, actually what you want to do is this is a packing problem. So instead of running all of these congestion controllers individually, what you really want to do is run one congestion controller and figure out, okay, my total bit rate is N. What is the actual collection of video feeds that I can fit into that bucket? So if I have 5 megabits available, I want to pack, I can pack 2 high feeds in there and 1 medium and stuff like that. And so that's what this new congestion controller is looking at, is like we have one bucket of available bit rate, and we're going to probe the same way that we did before by looking at the latency and looking at the packet loss. But the way that we're actually going to generate and pick the video is by having like this predefined bucket. So that was a lot like, and a lot of the gaps here are just I don't understand things. Like I'm trying to figure out things as I go. So if you're interested, like Pion is just a complete open source project. If you found some of these concepts interesting, we would love to have you. Um, you can come and build a career out of this stuff. Like a lot of people that have contributed have gone on and gotten jobs and other things. So we would love to have you. And if you're curious more about this stuff, we have the WebRTC for the Curious and Pion and Slack and available in lots of different places. So thank you so much. And yeah, and like that is kind of my mental model of you have the metadata, which is going back and forth between the clients, which is those receiver reports and those transport-wide congestion control reports. But then you have the actual congestion controllers that are running logic off of that metadata. So yeah, thank you so much.
Thank you very much, Sean. That's perfect timing. Our next speaker is Avery Penoran, and he's the co-founder and CEO of Tailscale. He's been a consultant to Alphabet senior leadership and led the Google Fiber's gigabit Wi-Fi and platform analytics team. And he has done many open source projects. So please, Avery, stage is yours.
Hello there. Can you hear me okay?
I can hear you very well.
Excellent. All right. Okay, well, as you might have heard, I'm Avery. I'm here to talk to you about a different kind of latency than maybe everybody else is talking about. It's a latency that's been around for so long we stopped even realizing it's there, and that's peer-to-peer latency on the internet. Once upon a time, I could FTP from any computer to any other computer, and I could get or put a file just like that. The internet was invisible. It felt like a direct connection from anywhere to anywhere. And obviously the latency, we had queuing problems, and a lot of people here are talking about the queuing problems, but fundamentally you could send a file and you can connect directly from one thing to another. Peer-to-peer is dead. It's been dead for quite a long time now. That's just not how it works anymore. There aren't peers anymore. Peers can't reach each other because we ran out of IP addresses and we put them all behind NATs and firewalls. So, of course, I know the kind of people who are going to be here. I have to tell you, there's a disclaimer. IPv6 will, of course, solve everything. I know what you're thinking. The root cause was we ran out of IP addresses. IPv6 has an unlimited set of IP addresses, problem solved. And that is basically true. As soon as we deploy it to everybody in the world, and we finally turn off IPv4, and we can finally turn off firewalls and NATs. That sounds nice. The first IPv6 RFC was in 1995. That was 28 years ago. I was actually in high school back then. I'm very much not in high school anymore. I still don't have IPv6 at home. Meanwhile, the world has changed. The 1995 problems they were setting out to solve in that RFC don't exist anymore. We solved all those problems the hard way because we didn't have IPv6. We have new problems. the problems we're not solving, we're not solving because we've been hung up on IPv6 for 28 years, right? The truth is, what we did instead of IPv6 was cloud computing. The wheel of time is turned on. We ran out of IP addresses. We worked around the fact that we didn't have enough IP addresses. Nobody has IP addresses anymore except cloud providers. So forget about peer-to-peer. We route everything through cloud providers. If I want to transfer a file, I bounce it through a cloud data center or at least a CDN, even if the two devices are sitting right next to each other in a cafe on the same Wi-Fi. We pay rent to cloud providers because they have static IPs and we don't. At every step, we pay rent. We pay to upload and download the files. You pay again to store the files. You pay again to run a server program that uploads and downloads and stores the files. And then if you forget to delete the file after you saved it on the server that you didn't even want the file on in the first place, you pay extra because it's using up storage for longer time. I never even wanted to store files in the cloud. I just wanted to send a file from node A to node B. But I'm paying all this rent and I added all this extra latency going all the way out to the cloud and all the way back. The whole internet is slow because we're doing everything through cloud providers that we don't need to be doing. And it's not just the IPs. In the intervening years, we all got OS firewalls and router firewalls, partly because of NAT and partly because of malware. More IP addresses don't even help anymore because we're also used to not having IP addresses that we've all gotten used to all the other problems. You need to open ports as well because we all have firewalls and NATs. You and I know how to open up ports. So it's a bunch of technical people here, right? But normal people don't know how to open ports. You talk to them about opening ports on their router. They're like, I need to call my 10-year-old who's going to explain this to me because I don't know how to do it, right? Anyone can connect to somebody's monthly subscription file upload and download service, but nobody can open a port, right? So now we pay money for what we used to get for free with FTP, just because it's so hard to do the thing we used to be able to do easily. And the third reason we pay rent to cloud providers is host names. Even if by some miracle, people could figure out how to get a public IP address and open a firewall port, they still couldn't actually find the other node because it doesn't have a name. Only servers have names anymore. Everybody knows that. That's just how it is. It didn't used to be like that. Everything was a host, everything was a peer, everything had a name, but that's not true anymore. Every client doesn't have a name. Without a host name, you can't even talk about wanting to send a file to node B. Who's node B, right? It's like 1984 Newspeak. If you don't have a way of saying it, you don't have a way of expressing it. Without names, we can't do anything. So I like to put this in perspective. The phone in my pocket is 10 times more powerful than the most powerful supercomputer that existed when the first IPv6 RFC came out in 1995. There was 170 gigaflops on at the time fastest supercomputer. I'm told that my iPhone 15 Pro Max has 2,147 gigaflops. Our idea of what it takes to run a server has gone way off the rails. Anything should be able to be a server. My phone should be able to be a server. My phone should be able to be 10 servers from 1995, right? Or 10 supercomputer servers from 1995. Obviously, the desktop computer server in 1995 that I was using was like, 10,000 times less powerful, right? It has nothing to do with battery life. It has nothing to do with RAM. It has nothing to do with anything. The only reason my phone can't be an FTP server that I can access from anywhere in the world is because peer-to-peer is dead, because IPv6 has left us hanging for 28 years. As you can tell, I'm a little grumpy about this. So anyway, summarize why I can't FTP to my phone. First one, IPv4. It won't give me a public IP address. Even if it did, I would have a NAT probably that would change my IP address. Firewalls then block the incoming connections. My server doesn't have a name, or my client, doesn't have a name, so I can't find it anyway, right? And the big one, the big thing that people in 1995 were thinking about but didn't try to solve, because they figured we'll just like roll out IPv6, and then after that's done, we'll start thinking about this problem. Computers move around, right? Back in 1995, you had a desktop computer, it was plugged into a physical connection. Nothing really changed very often. Nowadays, my phone changes its IP address whenever it moves anywhere. It hops from one router to another behind different firewalls. It hops from one cell tower to another. It hops between cellular and Wi-Fi connections. Every time it does, it has an opportunity to change its IP address. So even if I had a name, the name would be wrong shortly afterwards, right? It would be hopeless for something like dynamic DNS to try to keep up, because just DNS name caching latency is so long that I can't update my name as frequently as I change my IP address. So peer-to-peer has been dead for years, and it keeps getting more and more dead because we started with the problem that killed it, and now we don't even bother fixing the layers and layers of problems we put on top, because none of those things are actually stopping us from doing peer-to-peer. It was already dead. But now it gets harder and harder to resurrect it because now we've got this big pile of problems. So IP mobility, 1996, RFC 2002. Way back, came out only a year after the IPv6 RFC. People were already thinking like, I guess the writing's on the wall. It's possible that computers might no longer be plugged into the wall sometime soon. We better start thinking about what happens when computers start roaming around on the internet. So like, okay, we'll do it. They saw it coming. The original RFC 2002 was only for IPv4. It only took 8 years to get it updated to IPv6. Still no problem. That's long in the past. Well, there's one problem. What happens if you actually do it? So mobile IP does this thing where every device is a home network that owns its IP address. Then when you're not at home, people send the packets through your home router, and the router relays the packets over to wherever you are. As far as I can tell, this never actually got rolled out, but they were onto something. The relaying obviously adds latency, but it kind of worked, right? Big problem though was deployment. It was hard to deploy it because your home router had to support it, and router makers basically didn't care, right? This is something we learned over and over again with the IPv6 rollout, is the router makers don't care. Even if I would benefit from IPv6 and the server I'm connecting to would benefit from IPv6, everybody in between mostly was not going to benefit, or vice versa. Maybe it would make your routing table a lot easier if everybody was on IPv6, but it won't be a lot easier until everyone's on IPv4. So maybe everybody in the center of the internet really thinks IPv6 is the best thing ever, but there's no point rolling it out while everybody on the edges of the internet is demanding IPv4. And then they just have two networks. So this three-way market made it really impossible to adopt. Similarly with IP mobility, you had to have this smart router back at home that was willing to relay your IP for you. Nobody was willing to make these smart routers, right? The other big problem is latency. If my home was in California and I was in New York, and someone in New York wants to talk to me, it's going to get relayed back through home in California on the other side of the continent. Maybe Node A and B are on the same cafe Wi-Fi in New York. With IP mobility, it doesn't matter. It's going all the way there and back. Now that is latency, right? That's completely unnecessary, but it's what makes it slow. And it's also not how the internet was supposed to work when we built it. The internet is supposed to find the shortest path between two places, or at least the best path between two nodes, right? By some sort of metric of best. This is not the best metric, or not the best path by any metric I can think of, right? So here's the part that it took me a while to figure out, but somebody sent me a link on Twitter a couple of years ago, and it all suddenly clicked. I'm gonna have to give you some background. How did we get here? First of all, there's the OSI stack. I'm sure you've seen the OSI networking model. I always get confused about levels 5 to 7. I've never been able to figure out exactly which thing is which, so I'm just going to simplify it. Level 5 to 7, I don't know what each of the layers is, but they're obviously all inside HTTPS right now. And HTTPS runs over top of layers 1 to 4, leaving aside HTTP 3 and QUIC. But the ones I want to talk about for now are layers 1 to 4, right? Internet people like to make fun of the OSI model. The internet was sort of designed in spite of OSI. It was definitely not designed thanks to OSI. Internet doesn't really map perfectly onto the OSI layers, as you can see for 5 to 7. But there are some things that OSI got right and the internet got wrong, and we kind of don't like to acknowledge those things. I want to acknowledge it right now. So here's the link that somebody sent me on Twitter. It's called How in Heck Do You Lose a Layer? It's from the RENA project. They talk about what constitutes a good layer in a system architecture or a network architecture, which they claim is roughly the same thing. And this goes back to like Dijkstra's writings about architecture, which are pretty interesting to read. First one is a network layer should describe a separate scope from other network layers. In other words, don't repeat functions. So what that means is if one layer does something, don't do it again in another layer. So one weird mistake we made is that IP addresses are actually redundant with MAC addresses. Let me tell you what that means. Every interface has one IP address and one MAC address. I was confused about that since the very first time I touched ifconfig back in the 1990s. Like, why do I need two addresses? The answer is, in fact, you don't need a MAC address. It's historical craft, right? You can use an IP address instead. Now, are we ever going to get rid of MAC addresses? Probably not. But when you start thinking about it, every time we use a MAC address, we could have used an IPv6 address now that IPv6 exists, right? Now, we know for sure that these two layers are redundant because nowadays my phone just lies about its MAC address whenever it joins a Wi-Fi network, right? It's in the name of privacy. It's like, well, you can track me using my MAC address. I'm just going to make up one, and then I'm going to get an IP address, and I'm going to do all the rest of the work with my IP address. You might as well not have a MAC address at all assigned to the factory, right? Second rule for a networking layer, it should operate independently from all the other layers, and they call that modularity, right? So TCP is not a standalone module. I think we've probably all bumped into this in the past, right? TCP does not work with the IP layer. If your IP address changes, your TCP session breaks because your 16-bit port number isn't globally unique. That shouldn't actually happen. That is a violation of networking modularity. But you know what? The IP layer is also not a module. When I move from one physical network that's layer 1 to another, my IP address changes. Now that sounds like we're all so used to it that it doesn't seem like a surprise. But actually, if you look at every other layer, it doesn't work like that. When I move physical links, my MAC address stays the same. When I move physical links, my TCP port number stays the same. When I change IP addresses, my TCP port number stays the same, right? My HTTP host header stays the same no matter what changes. My TLS certificate stays the same no matter what changes. All the paths in my URLs stay the same no matter what changes. The only thing that changes when I change another layer, and when I change layer 1, is layer 3. They're glued together in kind of a weird way. And as a result, peer-to-peer is dead. Let me get to that. So this is where the paper that I linked to, how the heck did we lose a layer? They suggest like we're missing something that the OSI stack had that the internet stack did not have. So it's too late to fix all the layering problems. I think that's pretty obvious. You know, we had enough trouble rolling out IPv6. We're not going to roll out a complete change to the internet stack. But here's what we can do. IP mobility had it almost right. They added an extra layer with a fixed IP address, and they wrapped it up in the existing IP layer that has an unstable address. So the layer 3 is an interface address that changes depending on what you plug it into. Layer 3.5 is a host address that never changes no matter what happens. It's a separate module, it's completely independent, and it provides functionality that is not redundant with any other layer. So to make this work, all you need is a little service that maps host IPs to unstable routing IPs. I call that the control plane. And then you need something that can deliver these little tunnel packets directly where they're supposed to go, which is the network IP. Well, sorry, once you figure out where they need to go on the network, you can deliver them there and then the host can pick them up. So host layer routing is what I call this. And the thing we want to build that's different from IP mobility is you want to remap the addresses. You don't want to relay the packets, right? The purpose is to find out where the packet was supposed to go in the first place and then send it there. And yes, we still use a tunnel like IP mobility does, but there's no relay service. There's just a remapping service. That way, we don't need to change any of the routers. You don't need a home router that knows how to relay stuff. All you need is the ability for your client and your server to agree to use this new host mapping layer that will get the packets delivered where they're supposed to be. In the last 28 years, we learned how much router makers care about our problems, which is not very much. We had to get them out of this loop, right? Number 2, it follows the end-to-end principle. Upgrading the internet is really hard. Upgrading endpoint devices is much easier. We've known the end-to-end principle since the earliest days of the internet. Somehow we forgot about it. That's why IPv6 is so hard to roll out. But look how many versions of HTML, HTTP, TLS we rolled out during the same time. Lots of them. Even though there's billions of devices using these things, we were able to upgrade them incrementally because you didn't have to convince everybody to upgrade all at the same time. We can upgrade any server and any client to this new host layer routing thing, and they both benefit right away. You don't have to wait for anybody else. You especially don't have to wait for anybody in the middle. If I want to be able to FTP from my laptop into my phone, I can run this new layer right now. I'm the only one who has to care about it. And that's what makes it possible to adopt. That's what makes this such a useful layer. Third, it doesn't add any latency. That's why this talk is about latency, right? If you put it all together, you get this no added latency solution. If I want to SSH to my phone's host address, or if I do a video call with my phone's host address, I look it up once. There is a little bit of latency at the beginning, just like there is with DNS, and then I can connect directly to the device. No relays, no latency. So all we have to do is build it. So here's what you need. And I've tried to make sure that this sounds like less intimidating. So I because as a person who needs to manage engineering teams sometimes, I know how scary it can be to give people a big project. So as a computer scientist, I finished. We just need you to start working on it. Step 1, all you need, teensy tiny little real-time IP lookup service. That's what translates host IPs to internet interface IPs. Basically, just a distributed database. Nowadays, they're a dime a dozen. How hard can it be? You should probably put in some caching on top. Second, minor remapping layer for every OS. So probably want Linux, macOS, Windows, Android, iOS, a few BSDs, and so on. Probably you're going to be able to outsource that to contributors or whatever. I heard with enough eyeballs, all bugs are shallow. Anyway, no problem. It's just a small matter of programming. Third, and I hesitate to even bring this up, we all know it's optional. IPv6 is going to fix it any day now. A little bit of NAT traversal. NAT traversal, it's a little bit convoluted, but again, I linked to a helpful article about how that works if you download the slides. I wouldn't worry about it. Another small matter of programming. My estimate, you probably should be able to build the first version of this entire thing in a weekend, give or take. But in case you don't want to, I have good news. There's a prototype you can try right now. It's open source. It completely solves the IP mobility problem, and it adds zero latency. It brings peer-to-peer back to life. If you use this prototype, you can actually connect any peer to any other peer anywhere on the internet, no matter how many layers of firewalls they're on, regardless of whether it's on IPv4 or IPv6. It gives everybody an IPv6 and an IPv4 host address, whichever one you prefer, and it routes over everything. So it works right now. You can find it on GitHub at the link that'll show up in my slides, and you can send me any questions. And I think we might have a few minutes for questions right now.
Thank you very much, Avery. That's very, very interesting. We do have a couple. Do you see the Q&A?
Oh, I see a chat window that has a bunch of stuff in it.
There's a Q&A window as well. There is a question,
no,
but I don't understand
see that, I'm afraid. Do you want to read it to me? I don't know where to look for Q&A.
It says, how do Tailscale think about head scale? And I don't know what that means.
Oh, head scale is an open source clone of the Tailscale coordination server, which is the not open source part of Tailscale. So Headscale is great. We actually employ one of the developers and pay him to work on it part-time. The purpose of Tailscale is really what I just described in my talk. We are here to fix this problem with the internet, and it's really important that if you're going to fix the internet, the main thing about the internet is it works for everybody, right? We understand that not everybody in the world wants to pay Tailscale to use our coordination server. The internet itself, like lots of people made lots of money building it. They're continuing to make lots of money off it. I think that's very healthy, but it wasn't because one company owned everything, right? And so we're really happy about the Headscale project because it opens up this solution that I just described to everybody in a 100% open source way.
Cool. Questions are flowing in now. So Mike English is asking, how quickly can these mappings be updated to handle mobility? And can something like a TCP session survive that move?
Right now, the system that we have does real-time updates. So instead of doing actually polling plus caching, like I sort of described in the talk, because that's the easiest thing to build, we do push notifications to everybody participating. So once you've started talking to a node, you'll find out right away if its IP address ever changes in less than 100 milliseconds. And the answer is because, this is the second question, because you have a fixed IP address for the host, TCP sessions never get interrupted, no matter how much you move around.
Cool.
Or any other kind of session for that matter, because it's just like a fixed IP address with your fixed UDP or TCP layer that don't change.
Yeah. And then I think this is the final question. If one of the peers is run on browser using browser WebRTC, is layer 3.5 browser compatible, or are there any challenges there?
There is, let's see. So we currently don't support WebRTC in like our implementation, although that would be an obvious thing that should be added. There is a web implementation that's open source somewhere. I don't exactly know where the link is, but it's somewhere linked from that GitHub repository. And it uses WASM. So it's written in Go, but then compiled into WASM in a website. So I believe it uses, I'm not sure it's able to get direct point-to-point. I think it actually goes through a relay server right now. But with WebRTC, it could go point-to-point. You just haven't implemented that yet.
Cool. All right. Thank you very much, Avery.
No problem.
I think that's all the questions. So our next speaker is Francois Blanc from Meta, but we have to promote him to a panelist first. So give us a few seconds to fix that. There we go. So Francois runs the Metaverse QoE engineering at Meta. And it's time. So please, Francois, go ahead.
Good everyone, do you see me?
Yes, and we hear you. Thank you very much.
Okay. And I'm sharing my slide. I'm assuming you see it.
Yep, it's working.
Perfect. Good day, everyone. Francois Blouin here on behalf of the team that created this work. We're going to be sharing with you today a piece of work that was conducted as part of the TIP Telecom Infra project. And our focus area or subgroup is about QoE, QoS measurement framework and use cases. And we wanted to share with you some of the work that we conducted this year. And of course, if this is an area of interest and you would like to join this subgroup, please do so. So welcome, and I'll be sharing with you over the next 10-15 minutes our work. So in terms of agenda, we'll walk you through a bit of an intro, so to make sure that we're all talking the same language. Sometimes there is some subtle differences between quality of experience and quality of service. We'll present you the 5 steps framework that we have developed and give you a bit of an example and some of the insights for each of the 5 steps. We'll also cover a couple of use cases that we applied the framework, namely on short-form video and 3D volumetric calling, and we'll conclude then. In terms of definition, we would like to use the term QoE or quality of experience here for everything that relates to the end user. So I'm talking here about how am I satisfied with the service? How is the image quality, sound quality, video quality? Metrics typically will look into mean opinion score and maybe number of rebuffering and so on. I'm not talking about throughput and bandwidth at the QoE layer. QoS, on the other hand, is related to the infrastructure layer, and namely, we're focusing more at how we will deliver the service. And the metrics are different, the stakeholders are different, and here we'll be talking about latency, delay, and packet loss. So the big challenge now is how do we correlate these 2 distinct layers that sounds about the same, but they're quite different. And we'll be talking and try to provide you some insight through the rest of the webinar today. The main objective of our subgroup at TIP was to define what are relevant QoE metrics that one should use, what are the relevant QoS targets and metrics as well, and what are the tools and correlation methods that you can use to understand how these 2 dimensions are related. We want also to leverage this to have a kind of a common industry language, so we can unify content providers, applications providers, and communication service providers, understanding those metrics and understanding those trade-offs and being able to have the same level of understanding and language. We created this 5 steps framework, and essentially at the top we're talking about the defining those metrics. How do we define metrics at the QoE layer? Step 2 is we're going down now to the QoS layer, and we're looking at what are those metrics that are impacting the end user. Step 3 is about understanding the relationships between these 2 layers. Step 4 is about measurements. Where should we be measuring? What parameters should we be measuring? And in step 5, we apply the framework to 2 use cases, and we'll share some of the the early work in that. So starting at the top on defining metrics. So the first and most fundamental understanding is we need to divide and decompose the applications. And the process that we've been using is looking from three aspects. One is the human side, the system aspect, and the context related. So the ones we're mostly familiar is the system related. So system meaning the how that service will be deployed and what would be the typical impairments that you might observe from the system side, like you would observe like blurriness or blockiness, some speech distortion, some video distortion. If you're using 3D augmented reality, then we're going to be talking about motion to photon. So the system is basically the underlying devices, and that will be reproducing and delivering your service. On the human side, then we need to look into sensitivity to humans, to specific colors, a specific aspect of visual system, audio system that we have from the brain perspective. How do they matters to us as a human person? From the context perspective, now we need to look into how is the service being used, and how the user is using it. What is the surrounding environment? Am I at home on a gigabit internet access, or I'm on the road on my smartphone where sometimes the coverage might not be perfect, and we believe that expectations from end users varies according to how and where our customers are using the service. So it's important to factor that in defining the targets and the metrics. So we looked into a number of industry standards that have been published over the years, and we categorized them into four main group of applications. The first one being more voice related, voice quality, voice related, conversational voice, the video, the gaming, and 3D augmented reality. And we extracted from those standards the key quality of experience factors that matters the most from the end user perspective. And one thing to note here is, as you increase in the service, I guess, complexity, let's put it this way, in immersive 3D augmented reality, you can see that there are a number of factors that matters. In step two, we looked into the QoS layer. So we go one level down. Now we're trying to understand what could go wrong or what could be impacted when we start to deploy those services. And we broke it down into three main areas: from the user side, the network side, and then the content provider side, where you connect to a server in the cloud. And the blue and orange bubbles are representing the typical type of impairments that you would observe. The important here would be that QoE is end-to-end, so we need to look at it from the end-to-end perspective. We need to make sure that we understand what are those impairments, how big they represent, and in the next step 3, we're going to try to correlate if we add this amount of delay, then how it's going to be impacting my interactivity, and so on. Note here that some the blue, we color coded the blue bubbles that are more controlled by the content providers, and some are more influenced by the service provider or the communications telecom operators. In understanding the relationship between the QoE and QoS, this is fairly tricky and difficult. So there is no, I guess, simple answer to that. But what we found is there are a number of standards that have been published that are touching that subject and are providing good insights. And we categorize them for metaverse, audio, video, gaming, and telemetry. And as we start drilling into those standards, the video ones have a number of approaches or decision tree or approaches for correlating. subjective being very lengthy and complex, probably the most precise but not scalable, and objective methods are more suited for what we're trying to do here in doing correlation. And as we drill into the objective measures, there are full reference where you need the source and the playback video, for example, or you have the no reference where you can estimate the quality without the source of the material, which is the one that is less mature and has a bit more work to be done from the industry perspective. An example here of a way to correlate QoE to QoS for voice quality is a model from the ITU G107. And basically, it's a model where you can input the delay that you have in your system, and it will produce a scale from 0 to 100 called an R factor that will give you the quality of experience. On the video front, what we found out is most of the models are focusing at this point on the video quality, which is kind of the left side of this part, and also academic research, while the video degradations and video fidelity. And some new models now are starting to account for what we call the timeliness. When I say timeliness here, I'm talking about the loading speed to load your video, and if there are stalls or rebuffering. And for short form video, this is becoming an important factor because the end users are now watching videos that are 10 seconds, 30 seconds duration, and they're swiping typically very fast. Expectation is that the video comes and are loaded, preloaded, prefetched. And so we're listing here some of the no reference models that we found to be promising and interesting that we'll be exploring more. Step 4 has to do with the measurement aspect, and we wanted to apply the framework and try to see where should we be measuring, in which portion of the network. And this is a piece of work that we're still doing now, that is ongoing. And we're showing here a number of measurement points and what we think could be a series of measurement telemetry metrics that we can measure at these locations. As you can see, the list is still pretty substantial. So the challenge here would be to define which ones are more relevant to your specific applications. It's difficult to measure everything. It's also always the question of granularity of measurements, the time scale, and how do you synchronize all those measurement points together, such as data is available and useful if you collect at different points. So when we applied this framework, we have started to look now into if we apply this into short form video, like you can think about Facebook Reels, TikTok, YouTube Short. These are the kind of applications where now you're mixing video and you're mixing some level of interactivity. What are the audio quality, timeliness, temporal quality, spatial quality that would be important to measure and have in a model? That's what we have identified, and now we're in the process of defining what are the targets associated with this application. If we move to a more emerging and immersive service, such as 3D real-time telepresence, now we have also a different sets of metrics, again, covering the same kind of aspect. There are some obviously new metrics that are not necessarily applicable to short-form video. So there is now more of a sense of presence and immersion that we need to somehow measure, which will be a bit of a more complex and more novel. The real timeliness and responsivity of such systems in 3D augmented reality is now critical, because now we need to immerse ourselves, and the perceived delay from the brain and the eye systems is now very sensitive to the level of millisecond range. So in summary, in conclusion, we we need to meet the user expectations if we want to deliver satisfactory service, and to ensure that as we deploy these new or emerging services, we are accepting and understanding what are the expectations from the end users. And as we want to build our ecosystem of content providers and telecom operators who are delivering that, there might be ways to work together and collaborate more, and perhaps exchanging some level of information. We believe a top-down model, as we propose here, is desirable because we're starting from the end user's requirements and we're drilling down into the infrastructure to ensure that we meet these targets. So moving forward, what we would like to pursue and finish as part of our telecom infra project subgroup is to publish this framework. We have a white paper that is in review phase now, and we would like to finish the two use cases that I mentioned here briefly. And one more thing is, as an industry, we believe that there might be benefits from having a certain level of collaborations between the content providers and the telecom providers to either exchange some level of information, to calculate or extract what I call a no reference QE model, where we don't need the source. It's usually difficult from a telecom operators to have access to the video source. Although the content provider have that, can we exchange some level of metrics information about the given video? And we believe that would help unify and define a no reference metric that is suitable. So thank you very much. And I know it was a bit of a quick pace here, but I wanted just to give you a bit of a view of what we've been doing, and if there is any interest to joining our workforce, that will be greatly appreciated. Thank you very much, and I'll be opening up for any questions.
Thank you very much, Francois. So if there are questions, please submit them in the Q&A. Our next sort of session now is we're having a break until 10, how do you say that? 10 minutes after past. I don't see any questions right now. If you do have questions, you can add them either in the Q&A or in the chat, and we will get to them. But if there are no questions, we can... Oh, there we go. So Sauli is asking, maybe I missed it, but are there any latency targets for your main use cases?
There are targets?
Yes.
Yeah, so we haven't published yet the targets. That's what is ongoing now from the team. So we hope to include some of those in our publications in Q1 next year. So we as you know, there are some targets that have been established from the voice quality in terms of delay and expectations. When you exceed a certain amount of delay, which is around 150 milliseconds, the interactivity at the voice level now you're going to start seeing over talk, like two people are talking over each other. So on the voice quality, it's well known. On the short form video, I can say that what we observe is the loading should be, the prefetching or the preloading should be less than 1 second, generally speaking, and ideally you should not have any preloading or prefetch. So when you swipe your video, it's kind of instantaneous. In terms of immersive applications like 3D augmented reality, the motion to photon display latency, we're talking about in tens of milliseconds, between 10 to 50 millisecond max, where you're going to make sure that when I move my head in the 3D headsets, the image are also following. When I'm looking on the left, I'm not seeing the right image, etc., and that the brain. So these are kind of order of magnitude that we've been looking into some of the studies and publications that has been conducted.
Cool. That's a very strict requirement. It's interesting.
Yes.
All right. So now, thank you again, Francois, and we will now take a break for about 10 minutes, and we will be back.
Thank you.
Okay, so break is soon over, but we'll have a couple more minutes till we begin. All right. So let me introduce our next speaker is Joss Delbar from Airties. So Joss leads the Airties Smart Wi-Fi roadmap and has worked for nearly 20 years in the industry. And with that, thank you, Joss. You feel free to share your screen. I will stop sharing mine. Welcome.
Thank you, Bjorn. I hope you can hear me okay. Let me just...
I can hear you very well. And now your slides are also showing.
All right, thanks, Bjorn. Okay. Hi, everyone. Thank you for tuning in today. I hope you've had a good first half of the session today, and looking forward to the other days of the webinar. My name is Jos Delbar. I'm responsible for product management and data at Airties. And some of you may know us, some of you may not. Our mission is to help service providers, internet service providers, deliver great home experiences through our products and services. And our foundations have been Wi-Fi technology, Wi-Fi management, though our scope is in fact wider, going into the home, the full home experience, and also into the network. Latency is a relevant topic for us as well, in that role, in that mission. And we like to look at it from the perspective of in-home application quality of experience. So looking at a little bit at a more holistic level, how can we understand latency and how does it play into the home application QE management? So that's what I'll talk about today. I'll share a few words about why we think latency matters, what we see as key challenges and also key success factors for managing the QoE, and a few words about what we see as opportunities if this is done right. So let's start with the landscape. Obviously, latency isn't a new concept. The importance of low latency also isn't new. But we can say that in recent years, there's been a trend, an increased attention level on low latency. And there are several factors for that. One is the trend towards more remote working, which I think all have experienced here and accelerated during the COVID pandemic and has still continued afterwards. A lot of people, more and more people are using interactive applications, video conferencing applications, also co-authoring, shared documents, live editing, and so on. So there's been that factor for sure, which has, I think, increased the attention and the realization that latency matters. Then there's gaming. The gaming market continues to be huge, is growing. Online gaming has very demanding needs and tough requirements. And as well, you could see here in the picture, there's VR, which is, from a consumer point of view, we can say probably the most demanding application in terms of latency needs. So that's also starting to become more prevalent. There's more attention in the market. It seems to be breaking through. So these are some trends, some reasons why latency matters. And then Wi-Fi, our core business, Wi-Fi technology has for sure also followed those evolutions and is also geared towards improving speeds, increasing speeds, reducing latency for sure. with Wi-Fi 6, Wi-Fi 7, there's been some key technology additions that facilitate that. I'd like to add also that in our opinion, this element of latency is also interesting for service providers to use as a differentiation and to change a bit the differentiation away from pure speed. I think, at least let's say the perception I have is that a lot of people, when they look at these new plans, fiber plans, increased speeds, a lot of people kind of have the impression that, yeah, why does it always have to go faster and faster? I have enough. I think a lot of people still think of broadband as purely of that kind of the classic file sharing kind of use case, when they see, I don't need that extra speed. But if you take the angle of latency, I think that's an opportunity for differentiation as well. So in a nutshell, we see growing usage of latency sensitive applications, and that drives a need for more low latency networks. I'd like to also talk a little bit about some technologies, and there are many. I will go into one here. So some technologies that help to reduce latency and let's say assure the performance of certain key applications. What we have here is we have a trial we ran under the WBA end-to-end Wi-Fi QS group, where we evaluated the impact of SCS, a stream classification service, which is in the end about applying tagging and WMM tagging to applications on Wi-Fi. We created the test setup where we evaluated two more latency sensitive applications. One is cloud gaming, GeForce Now. Second is live streaming with Twitch. And in this setup, we evaluated different parameters to see and to prove the impact of prioritization to guarantee the application quality. You can see as in this setup, we put a quite demanding traffic pattern in place. We have several clients here connected to the Wi-Fi router with TCP and UDP traffic bidirectional. We also saturated the network with interference to create suboptimal conditions. And you might think, well, in real life, we'll never get into such conditions. Well, that's not necessarily true. In fact, if you think of a real home network with many clients, with clients also not in ideal conditions like here, but spread across the home, you will more easily hit the point where you get into congestion, and these technologies actually do make a difference. So we built a setup and we evaluated the impact of standard queuing and let's say no tagging, just best effort traffic versus classifying this traffic under video and voice categories through SCS. And we can say that, yeah, indeed, significant improvements are possible by applying prioritization. On the left-hand side, you see the results on GeForce Now, where we're plotting here on the x-axis the delay. Mind you, this is a logarithmic scale on this one. We're plotting the delay on the x-axis and then the probability of achieving that delay on the y-axis. So we've been interested here in the 90th percentile, the 90th percentile, which is the blue dotted line. And we can see here in blue, the blue lines here on the left, the delay is quite low in case of a prioritized traffic. But interestingly, with GeForce Now, if you don't prioritize, you see this second blue line here in the middle, there's already a significant delay in that test setup already. So we have a good coverage client, pretty strong network in let's say load on the network, and already there, GeForce Now is starting to feel that, and prioritization helps to improve the delay. So this is an application, cloud gaming, which is very, let's say, latency intolerant, and where prioritization has a strong impact on the performance. And obviously then in red, if you start making the conditions worse by increasing the distance between the clients, that decreases the data rate, increases airtime usage, you see an even stronger impact. On the right side, with Twitch live streaming, Here, the delay is not logarithmic, it's a linear scale. You can see there's also an improvement and an impact, but it's less. And that's because there is a bit of latency tolerance in this application due to some buffering. But it is live streaming, so the buffering is limited, and you do see an impact as well, a positive impact if you apply prioritization, but it's only really necessary when conditions deteriorate. So we can say that the more latency intolerant applications you get, obviously, it's quite obvious, and we're not showing VR here, but we know that that's even more stringent, the more important it becomes to manage the latency. And it will be noticeable to the end user. This delay is noticeable. I'm not showing it here, but also, for example, the video resolution is impacted. In order to maintain a HD or 4K resolution in cloud gaming, for example, you also need these techniques. So we can say, yeah, there is a solution. There are technologies that can help. But of course, this is a lab environment. This is still a relatively simple case. And we'd like to also talk a little bit about what we see as challenges when applying this in a more holistic context, and what we also see as success factors to making this deployable, to making this viable from a business sense for ISPs. So the first challenge I want to highlight is that in practice, a household is more than one device or more than one application. The test results I showed previously are all about one application. And if one application wants priority, well, then it's easy to give it priority, and it will get priority. And then we can say, yeah, problem solved, job done. But we know that, in real life, it's more complicated. There are multiple devices and applications potentially running in parallel. And we can expect, that multiple applications will also start requesting priority, perhaps. And they all want the best for themselves. But I can say, and also as a product manager, I'm very familiar with this. When everything is a priority, then nothing is. So that challenge, we believe, needs to be resolved and can be resolved through orchestrating the home network and the latency management inside that home network. Now, orchestration, what does that mean? Well, I'm talking about things like understanding what devices and which applications are running. It's very important. Without that understanding, without that awareness, it's very hard to make decisions, of course. I'm talking about measuring the application quality and not just the latency, but really understanding what that means for the application quality, and understanding also the problems and the root causes and the diagnostics in case things are not good. So you need that device and application awareness to understand what's going on. You need to be able to measure the quality and understand what's causing the degradation in order to act. And then also with orchestration comes decision-making and potential conflict resolution. If you cannot give everything priority, you may need to make choices that may be rule-based. You may involve the user in this decision, or you may try to automate that and only bring it to the user's attention when there is no ideal solution. So that's the first challenge, a very important success factor, we believe, in bringing this to market. A second point, the second challenge is that there are multiple network technologies at play here. And I mean both, let's say, vertically. There's the physical layer, there's the Wi-Fi mechanisms, there's tagging, there's queue management, there's assured services, but there's also the application layer. And then there's a network element, the end-to-end approach at play as well. So we see a lot of interesting technologies, a lot of interesting standards boiling up, and we think that's very important. Success factor is to have standardization where solutions can rely on to just make it all work when we have all these different technologies working together. But it's not going to be simple. There's going to be legacy involved, alternative competing technologies in place. But it's important to have standardization, and we're strongly supporting that through WBA and other initiatives to make that a reality. End-to-end approach is key. When you think about the home network, the applications running there are usually connected to the access network and the broader internet, so it's important to have the end-to-end view. And then, of course, the ability to influence the whole stack. When we talk about Wi-Fi, it's not just about one element, it's also tied into the channel management, the steering, all these things drive the end quality of the application. And all of these things affect latency in some way. And the last but not least, a challenge we see also is that this is all terribly complicated. And it's not so obvious to provide visibility in a simple way, which is what users and operators expect at the end. They just want to get the job done. They want to have an enjoyable experience. Don't want to be confronted with all, let's say, all these things. They don't want to configure all these things and have to dial and change the levers. So the success factor there is automating that as much as possible, but also providing visibility about what's going on and being able to explain what's going on to still make it tangible for the different stakeholders. When these things are done right, when, let's say, these challenges are addressed, we believe that there are opportunities with latency management and application queue management in general to enable new propositions in residential markets, in business markets as well. For end users, for consumers, if this is done right, you can have an enjoyable experience, a more enjoyable experience with these key applications that they care about: online gaming, VR, high quality video, live video. We also see a proposition around personalized experiences. It's important to, although, as I said, it's terribly complicated, to give users and consumers a view of what's going on, the ability to tweak the performance according to their wishes, according to their needs. And that will also give people a sense of control. They deserve that. And also it can help with stickiness for the service provider if they do it in a nice way. For the service providers, this field provides new opportunities to come with new use cases for their customers. As mentioned in the beginning, helps to shift the narrative from broadband speeds purely into more things, latency, application quality, and that can be a churn reducer for service providers and possibly also upsell opportunity. And to make that upsell opportunity real, it's going to be very important again to be able to easily but clearly explain what's going on in the network, what the service provider is helping you to do to manage that experience. And then last but not least, we also see opportunities around for employers, for enterprises, tying back to the work from home trend, the remote working trend. It's going to be, I think, very interesting for employers to have solutions that can improve productivity around these applications, video conferencing, co-authoring, and that will also help them align the environment and kind of the experience between on-premise and remote. So to conclude this short talk, from Airtime's point of view, we can say, yeah, we see, I think, just as everyone here on the webinar, this need for low latency networks is definitely increasing, and there's more attention on that lately. We are aware and conscious of many different technologies and standards that exist that can reduce latency through different mechanisms. But as well, there are challenges to manage all this at scale when you think about the holistic aspect of application QE management. And so those challenges, when addressed in the right way, when done in the right way, there is an opportunity to enable new experiences, new propositions for both consumers and enterprises. So thanks for listening. I hope you have also enjoyable session the rest of these days. For those who are interested, I invite you to check a few references here on the slide. We have a few white papers which you may find interesting around ensuring Wi-Fi QoE. There's one on our website. There's also one co-authored under the Wireless Broadband Alliance. And last but not least, also for those looking to a little bit more details, I invite you to check a research paper around bridging the gap, the QS gap in Wi-Fi networks on IEEE. So thanks once again. If there are any questions, just shout.
Thank you very much, Joss. We do have a question. So Frank is asking, there's a rumor you guys at Airtypes are working on getting FQ Cuddle Cake deeper into the hardware. Can you give us some update on that?
Yes, of course, I cannot comment on rumors, Greg. But thanks for your question. I think I'd be curious if you could say where you picked up the rumor, but I can probably put you in contact with some of my colleagues who may be able to liaise with you and share more on that.
Yeah,
so
you should
I'd
be.
invite you to drop me a message on email. Frank, I can give you my details, and I'd be glad to follow up with you.
Cool. And then we have time for one more question. So how fast can the QoE detection running at higher layer roll down to lower layers and make an impact?
That's an excellent question, actually, and I think the answer is fast. We have let's say, emphasized in our own developments in Airties on being able to detect applications in real time. And what I mean by that is detect as soon as an application starts that it's running, and that's important because the early phases of an application can already be, let's say, so key for user experience. You may know the saying, like, the first impressions are made, you know, or how should I say? I should say differently. You can change the first impression once you made it. It's very difficult. So it can be done very fast. You can apply these prioritization techniques, for example, I mentioned, very quickly, and they do have an immediate impact. Other techniques, of course, they rely on multiple chains or links in the chain. There may be some propagation delay, but it can be done very fast. And in fact, it's essential to act quickly.
Right. Thank you very much, Joss. We have to move on to our next speaker now. Thanks for the questions, everyone. Our next speaker is Ermin Sakic. Am I saying that correctly?
You are pronouncing it correctly, Bjorn. Yeah.
Thank you, Ermin. He's a software engineer at NVIDIA and has been working on, among other things, their cloud gaming service, GeForce Now. So, Ermin, the stage is yours.
Thanks, Bjorn. So, hi, everyone, and welcome to my talk on latency and cloud streaming. Bjorn, just a quick confirmation, you can hear and see me well, right? The screen.
I can hear you well, I can see your slides,
cool.
and I can see your video as well.
Perfect, thank you. So yeah, welcome to my talk on latency and cloud streaming. My name is Ermin Sakic, as Bjorn mentioned, and I'm a software engineer with NVIDIA working on the streaming SDK, where I focus on achieving quality of service and cross-layer optimizations for our video streaming stack. And today I will be giving a very quick intro to cloud streaming and discuss some challenges that we've been facing with making the cloud streaming operate well at scale and over today's internet. And we'll also show some new production data here from GeForce Now, which is our prime cloud gaming service. So without further ado, so for those who are unaware, cloud streaming, was there a question or comment?
There is a question in the Q&A, but I think we can take them after the presentation.
Sounds good. With cloud streaming, basically content is rendered remotely by a remote GPU, not on the client's device. And the idea is that on the server side, we're basically generating the frames and encoding the frames and sending them over an unreliable link, network, internet, towards the client for decoding and displaying. And clients this way deliver high fidelity. Clients can this way get high fidelity content and interactive content delivered to them while having a lightweight hardware spec, and so minimize for weight and power. And the application vendors also benefit from this because now they can build their content, prepare their content, optimize it for one platform, and make it available across most relevant platforms on the market in a straightforward way. So with NVIDIA, we have two products or two kits in this domain. Cloud XR SDK is basically something you can use to build your XR streaming applications top of. And then there's also GeForce Now, the cloud gaming service, which has millions of users. And so both of these at their core use the same streaming SDK that I will be referencing throughout this presentation. So before we dive into the network aspects of latency, I just wanted to quickly, point out all the other sources of latency that in some cases are become equally important from perspective of users' experience and from perspective of measuring the system latency. And I'll quickly skim through those. So on the controller side, based on the client side and client's network, we capture the controller inputs. And we send those inputs over to the server. And depending on the controller type, connectivity, and uplink speeds and latency, this can take a while. On the server side, we basically have a game running, and we are injecting the controller input. We are simulating the game state. And GPU gets tasked here with rendering a fresh frame based off the game render queue. And this takes some time too, because we have to run at the pace of the game engine. The video streamer will capture the game render output, it will encode it, and it will start streaming the audio plus video packets over to the client, perhaps even applying packet pacing in the process to address some lossy conditions. And this will add some additional latency. The traffic will traverse internet, reach the client, and then the client, when the client receives the data, it will decode the frame and put the frame into render queue. Now, depending on the client speed, decoding takes time, and there's also the post-processing, for example, upscaling. We have a couple of techniques there too, that will also add some small delay to the process. And finally, on the render side, on the client side, we will pick up the frame and from the decoder queue and present it at the next vsync interval, which means that we also have a monitor's refresh rate as one of the delay sources. So in an attempt to overall reduce the end-to-end system latency, we do use here a couple techniques. So first, we can stream content at very high FPS, 240 up to 240 FPS to present the freshest game state to the client, so to not show outdated content. At 240 FPS streaming, we also, for select games, we can deploy NVIDIA Reflex, which is basically helping us remove the back pressure from the CPU and the GPU and keep the server render queue from which we sample the rendered content by the GPU minimal in size, or usually no queue. And on the client side, we have also a couple mechanisms. So we have adaptive vsync and digital buffer, which basically help together align the game render with the monitor's vsync interval. And this helps us eliminate any extra wait latency between the decode timestamp and the render timestamp. And when there's network jitter and when there's variable input of decoded frames to decoder, there's the digital buffer can also help with that. And that's kind of at very high level. Focus of the talk, however, today is in the networking itself, and we will look at the delays there. Network latency in general impacts customer satisfaction. We know users and press notices the impact of network latency in cloud streaming. So what we see here on the right chart is basically on the green line plot is that user ratings on the y-axis, they correlate inversely with the round trip delay percentile 99 metric. You can think of round trip delay as something reminiscent of an RTT, but at per frame level. So basically, users get more unhappy when they have higher latencies, especially also here P99 I'm showing. And there's a rating drop approximately of 20% from the highest to the lowest point here. Fortunately, we do see that the majority of our sessions do have P99's RTDs well below 100 milliseconds at 20 to 30 millisecond range. I know this is in the blue plot, so this is basically like a distribution of the P99 RTDs. But there's still here a very long tail that we want and straight to improve. And I will now quickly show where the long tail might come from for us and what we're trying to address with the quality of service and with adaptation on the sender. So well, let's briefly look at these. So on terms of most obvious impact on the user experience, it's the stutters when streaming interactive content. So stutters usually come from packet losses and from very delayed frames. And Packet losses come for various reasons. So due to tail drops in the wide area network, what we're seeing frequently, AQM drops in the user's network. And then there's obviously also interference in users' access networks, so Wi-Fi or RAN. And for addressing lossy links, we do rely on NAC retransmissions that come with the penalty of additional delay in frame assembly. Then there's also loss-guided center bitrate adjustments, basically decrease the streaming rate when we are observing losses and tail drops. And then there's also forward error correction, which helps us with recovery at minimal or no expense to latency. We do support Reed-Solomon FEC and XOR-based Flex FEC encoding in the products, but there's a lot of details there. If you're interested in how GeForce Now implements the Flex FEC, there's an in-depth presentation on that on another conference by one of my colleagues. So this will be in the slides linked. We also can encounter queue buildups and buffer bloats very frequently. So for this, we do track one-way delay and one-way delay gradients that help us adjust the streaming rate, again, on the sender in combination with the loss. And additionally, we do make use also of bandwidth estimation here to cap and not exceed estimated bandwidth at any point in time. We also do see ISPs that are still throttling out there in the internet, and we can estimate basically rate limit caps and pace our packets appropriately to stay below the threshold so we would incur losses due to throttling on select ISPs. And if everything fails and we still cannot assemble the frames and we lose enough packets, we can always try to visually conceal the frames for minimized impact on streaming experience and latency, but there will be some impact on the visual experience. Or we can request new iframes, and this will, of course, add up some delays. We do expose the users a lot of flexibility with adjusting each of the configs I mentioned before, reflex, HDR, adaptive VSync, and so on. You can set also resolution max bitrate, but you can also enable or disable the adjustments for poor network conditions, which would affect the streaming bitrate adjustments, FPS changes, video resolution adaptation, forward error connection, dynamic FEC, and so on. So users have the power to see how bad or well their network would perform without this. So going now to the main topics, connectivity issues. We have 100+ countries covered by the service, and we have data centers in 30+ physical locations and a lot more logical zones. We do know that we have like separate peerings and points of presence of various IXPs. We do know that increasing the coverage and increasing the count of zones and carefully selecting the peers helps with decreasing the end-to-end network latencies. So we do see also, however, still ISP peering bottlenecks, and this can impact our loss rates, and this is what impacts the users. And so interconnects between ISPs and eyeball ISPs where the users sit they are not in our control. So we always aim to observe, identify, and react to the peering bottlenecks. And this is how we're doing it currently. So we learned over time that AS path length metric, BGP selection, while it is important, it isn't really the main metric we should be routing our traffic by. So in the past, in special cases, when we would try to optimize for QE on select eyeball ISPs, we would do something like AS path per pending if the eyeball ISP would be large or important enough to warrant that. But this was a hands-on process, and we had to scale away from that. Additionally, the other observation, except for the increased efforts for QE, if you're doing it manually, we also see here on the example of user rating heat plot that users don't always really care about achieving the minimum network latency. They may rate their streaming experience as good as long as they have a sufficient throughput and consistent throughput and latency, and as long as the latency is not too high, depending on the game type again, and not too varied, basically. So knowing this, we started, instead of optimizing for shortest path, we started assigning our transit options scores and our transit peers. and calculating across multiple networking and throughput metrics, what would be the best path to take for a specific aggregation that we are targeting with our packets. And this could be, ASN and some netmask segregation, or even a single user. So we update this state dynamically and every couple hours, and we adapt for anomalies if there are spikes and some sudden changes in the internet. So this allows us to override BGP path selection fully. And the example here, I'm showing top 3 ISP in Europe that after deployment of this approach basically saw a 30% latency decrease compared to the shortest AS path when using the QoE routing. And in addition to latency, we do see that this can also bring us extra bitrate improvements because we can now stream at higher quality. And we also do monitor anomalies, as I mentioned before. So if you had an unexpected transit bottleneck, there's, say, Champions League game running, and there's a lot of streaming towards specific ISPs. This can cause bottlenecks and loss, and we are able to detect this now on the fly and reroute the traffic fully dynamically without SRA involvement. Yeah, so since couple weeks, since couple months, we are auto steering traffic towards a very vast majority of our eyeball ISPs and across 30 plus data centers. And last topic. So when it comes to handling last mile issues, this is also important for us. We have to fight buffer blows, packet loss. And one of the efforts here was to standardize a low latency enabling AQM in Alpha-RS framework, you might know that. And the goal is to reduce latency for responsive senders. So for us, it meant needing to transmit congestion notifications from client to streamer, as well as being able to react with aggressive sender rate adaptation and aggressive pacing when there's significant congestions occurring somewhere on the path, usually in the user's network. And so Cloud XR 4.0 SDK is this is the XR streaming solution. You can basically already get and use with Alpha-RS CC support. And we are also prototyping GFN support for Alpha-RS. So I'm showing here quickly 2 results. We have a couple ISPs that we're experimenting with and could already confirm significant improvements from using Alpha-RS in combination with cloud streaming. So tests here on they are kind of very aggressive. So we have 8 to 10 unresponsive TCP cubic flows on uplink and downstream. And an example of a DOCSIS operator here on the left, I'm showing that black is the Alpha-RS enabled GFN, blue is the non-Alpha-RS one. We see a P99 latency drop on uplink by 85% and 24% average round-trip delay drops when deploying Alpha-RS AQM instead of DOCSIS PI. This specific case, this is only uplink, and uplink is here very important because it's a MICE flow, but it carries congestion stats and game control packets, and so isolating this really makes out for important user experience. And on the right, we see another ISP, again with lab measurements, a similar setup, so 10 TCP cubic congestions on upstream and downstream this time. And when relying on a single QAQM, we see a very large latency spike when adding that cross traffic. We, after dropping the sender rate and after seeing some packet losses in addition to the latency increase, even after dropping the sender rate, we are basically still losing a lot of packets, which are here represented in red, because we don't really have a queue isolation. And so if we are dropping the streaming rate, some other greedy flows will pick up for the throughput and optimize for capacity at expense of delay. So no real benefit here, and only if we add Alpha-RS, then we start seeing that with the dual queue AQM as per IETF and low latency DOCSIS spec, we do see directly a 72% RTD drop in the same scenario, close to base latency, no outliers, and we also completely work around the packet loss and stream at the target bitrate, which here is well below the allocated fair share. So this was a 360 megabits downstream link with 10 TCP flows and GFN. We also are very happy to have FQ cuddle or cake on the path. Definitely, so whatever it can provide for Q latency isolation, but we also do see a benefit in having a congestion signal instead of a loss-based signal in general, because it causes less stutter for the user. And last slide, So we did see that there, in terms of ECT1 marking penetration and very limited geographical regions where we measured this in ABs, there are some issues. At very high level, we do see consistent ECT1 marking for majority of our sessions. So approximately 94% of our traffic gets the ECT1 field piped through. But there are still some tier 1 providers that suffer from ECT1 bleaching. There are also client ISPs that suffer from ECT1 bleaching. And I'm redacting here the names, not the finger point, but basically we did reach out to these impacted providers, and we could confirm either router configuration issues or individual NIC equipment in their setup causing issues such as bit flips of the ECN header field. And they are working on solutions. So fixes are in progress, and we are hoping that the last 6% of the streaming session that currently do not get the ECT1 piped, I will eventually get that, and our users will actually eventually be able to benefit from Alpharez equipment if they got it in their network. And with that, I will wrap up and thank Domos for inviting and for organizing the event. I'm also inviting the audience to test out either solution here. We have a free tier for GeForce Now too, and feel free to reach out with your experiences, observations of congestion control or any measurements. Thank you for listening. Back to you
very much, Ermin. That was great. We have a few questions. I think we'll try to get to a couple of them. First, Wojciech is asking, do you know what kind of throughput estimation NVIDIA is using with GeForce Now gaming streaming service?
We have our own proprietary algorithm for that. Basically, we consider things such as pause due to pacing breaks, the inter-receive times for individual packets on the receiver side, and all that.
Okay. And then another question is, how do you decide to trade off resolution versus frame rate versus bit rate when you need to adapt to slower network speeds?
Right. It fully depends on the type of baseline where we're adapting from. So, for example, when switching between 60 and 30 FPS, this will be the very last thing we would do. Like we would before that switch dynamically the resolution multiple times. And when we are streaming at higher rates, say 240 FPS, 120 FPS, we in fact do start dropping to higher thresholds, like 90 FPS, for example, from 120, before we would start decreasing the resolution. It's something what we also had, of course, our QA and pro gamer confirmed that this is the best works for average gamer, because it's less noticeable to drop from higher FPS compared to lower FPS settings.
Cool. Right, thank you very much. There are a couple more questions in the Q&A. So if you have time, it would be great if you can get to those as well. We have to move on to the next speaker now. So
thank you.
Thank you very much, Sherman. Our next speaker is Will Penson from Conviva, and he leads the product strategy there. And Conviva is a company that works with content providers to measure and improve quality of service and quality of experience. So Will, please take it away.
Thank you, Bjorn. Good afternoon, good morning, depending on where you are.
We can hear you loud and clear.
You can hear me?
Yes.
Good. Let me share my screen and let's bring up my deck.
There we go. We can see your slides as well.
Go. Hopefully you've got the full screen there.
Yep, it's working well.
All right, wonderful. So yes, my name is Will Penson. I'm in product management at Conviva. It's great to be invited to speak today. What I'm going to cover in the next 20 minutes or so, I want to talk about the significance of latency in video streaming, drill down into some of the contributing factors to that, and then talk about best practice for measuring that and optimizing it. And then looking forward to some future technologies that are coming down the pipe that should enable us to bring it down. Just before I go into that, just a little introduction on Conviva. We've been around for about 16 years now. Our historical focus has been on streaming analytics for video publishers. We work with 8 out of the 10 largest global media conglomerates on the planet, and we measure about 220 billion video streams every year. So we have a lot of data related to video streaming and video consumption and viewer experience. So Let's talk a little bit about the significance of latency in streaming video. So it's probably an obvious statement these days, but video dominates the internet. It now accounts for about 82% of total internet traffic, and it's growing about 15% year on year. And last year, 2022, was the year in which streaming viewership overtook traditional broadcast. And then within the sort of global streaming footprint, about 25% of that traffic is live streaming. It's obviously where, live streaming, where latency is most relevant. So, we're talking about a problem that's relevant or sort of representative of 20% of global internet traffic. The challenge, of course, is the internet was not designed for video. Traditional broadcast networks were purpose-built for delivering video, and they were built to do it at high scale with very high quality and key with very consistent and low latency. And I think it's both the low latency and the consistent latency that's important there. So now we've got these two delivery networks operating in parallel with very inconsistent viewer experience, and that's starting to drive some significant viewer frustration. So the most sort of obvious triggers you would imagine for latency in streaming relate to sports and live news, particularly sports, right? It's that scenario where you get the push notification on your mobile whilst you're still watching the game and it gives away the end result, or you're hearing the screams and the cries from your neighbors giving away the goal, and the ball is still halfway up the pitch. So these are probably the most sort of obvious scenarios, use cases you think about when you think about latency, but there's actually other industries which are highly dependent on low latency too. In fact, others that where it's absolutely critical. These industries do not function without super low latency. So industries like betting and gambling, or esports, or auctions, or education, or teleshopping and live commerce. So there is an increasing need to bring latency down to sub-second and make it really consistent with traditional broadcast networks. So let's talk about some of the contributing factors for latency in streaming. So let's take a look at a typical video delivery chain, and this is a relatively kind of simplified architecture, but it represents a glass-to-glass view, right? So from camera all the way through to the end user, through to the screen. And you can see there's various links in the delivery chain here. So we've got, and I'll go through these in more detail shortly, but we've got encoding and transcoding. We've got packaging, right? We've got an origin server, which is essentially the depot before the data leaves the building. And then we've got our network of cache servers, our content delivery networks around the country, around the globe. We've got our last mile, and then ultimately we have the client, right? The applications and the players. Yeah. So let's drill down a little bit more into the detail here. So these are the sort of components that can contribute towards latency. And if you add all of them together, then you can add well over a minute of latency compared to traditional broadcast delivery chains. So you have challenges with encoding and transcoding, right? Which compression standards are you using? The complexity of the profile that you've defined, right? How many different devices are you trying to deliver to? What's the range of renditions that you're including in your video profile? Are you doing encoding and transcoding on premise, or are you doing it in the cloud? When you are splitting out a video from a monolithic file into the smaller chunks that are more appropriate for internet delivery, there's all sorts of variables in terms of which protocol you're using. You're using a traditional protocol like an HLS or a Dash, or using one of the new standards like WebRTC or low latency HLS or HESP, for example. You have the segment size to consider, right? If you're using a sort of traditional 10-second chunk size in your packaging, then you've automatically introduced a minimum 10-second latency into your video delivery chain. And then, of course, we've got security standards to consider as well. So if you want to secure that content, if you want to run it through DRM encryption standards, that's going to add a degree of latency as well. And this is all still in the head end, right? So getting from origin to cache, you've got factors such as the distance to those edge servers, the load on those CDN servers, any network congestion, the various different caching policies in place, and then which transport protocols are in use. And then in the network itself, right, once we've got past peering, we've got into the ISP layer, we've got network congestion to contend with, we've got peering agreements, we've got routing efficiencies, we've got DNS resolution time. So there's a lot in the network. And then even once the video has reached the endpoint, right, it's reached the client application, there's still many variables there, right? You've got the performance of the hardware, its ability to decrypt and decode that video, the various different buffering settings which are implemented on that video player. Which codecs does that device support? And that's going to determine, which of the many different sort of variations on the stream which are available that it's going to attempt to play. So there's a lot of different variables in here as well. And then in addition to that, you've got advertising, because you need to monetize this content. One of those common mechanisms for that is advertising, and there's various different mechanisms available there. So some streamers use client-side ad insertion technology, others use server-side ad insertion. There are different ad creative sizes and complexities. There's different caching strategies. Some ads are preloaded, others are not. Some servers are more responsive than others. And then if you want viewability metrics, if you actually want to be able to measure how many people saw that ad, how long they watched it for, even the measurement itself can introduce additional latency there. So there is a significant amount of complexity in the video delivery chain, and there's a lot of opportunities to introduce additional latency. So let's talk a little bit about measurement. So how do you quantify latency, and how do you isolate root cause? So let's come back to our video delivery chain diagram here, and let's break it out into the various sort of component parts, right? The links in the chain. So you can see there's a number of distinct timestamps built in here, T0 through T6. So T0 to T6, that represents the end-to-end streaming latency. That is the glass to glass. And that is a useful figure to know. Ultimately, I guess that's what matters to the end viewer. But it's not necessarily that actionable, right? You want to be able to drill down and understand what are the contributions at each point in the delivery chain. If 90% of my latency is coming from network, there's only so much that I'm going to be able to do in the head end, for example, to bring that down. So T0 through T1 represents the encoding latency. That's the time it takes to encode and produce the live stream. T1 to T2 represents the transcoding latency. So this is the time it takes to transcode the live stream into the multiple adaptive bitrate streams, right? We have to do that for the video, for the audio, for the text tracks, for the subtitles, and so on. And then we need to do the packaging, right? So there is a packaging latency. So this is the time it takes to segment, stream, and produce an HTTP package, right? So we would sort of typically measure that from until the segment file and the manifest have been published to the origin server, right? That would be your T2 to T3 interval. From there, we then need to deal with T3 to T4. So this is the publishing latency. So that's the time from segment creation until the time that it's available on the origin for request from a client device. T4 to T5 represents the CDN delivery latency. So that's the time between the segment request and the delivery of the first byte of the segment at the client. And then, as I covered before, T5 to T6 represents the rendering latency, right? So it's the time between the client actually receiving a video frame and then being able to decode it, decrypt it, and render it within the video player. So what we really want is a mechanism that can measure each of these different distinct points and break down that overall latency into something much more bite-sized and much more actionable. So let's talk about some of the measurement techniques that are available. Let's start low tech, right? Option number one is the digital clock application, which is very literally film a clock. You film a clock, you see what the clock says on the wall, you see what the clock says on the screen, and then you deduct the two. And this is probably the most low tech, low scale way of doing it. But it is still a way of doing it, and it works in a test environment. But this is obviously not a production scale technique, and it still really only tells you the end-to-end T0 to T6 latency, so it isn't the most actionable. The sort of cousin of the digital clock application is timestamps, whereby a visual timestamp is embedded in each frame. And you can do this at various different stages in the encoding, so that can break down the latency into a couple of distinct points in the head end, but it's still a relatively limited way of doing it. And of course, it doesn't work in production because you don't want your end viewers to be seeing lots of timestamps scattered around on the screen. So these are both very much kind of low tech and sort of QA environment techniques. The next two techniques are much more scalable and appropriate for production scale video publishing. We have sensors, and so this is where agents and SDKs are embedded throughout the delivery chain, and that enables you to measure the latency at distinct points. And then quite closely aligned with that is a technique called fingerprinting. And again, this is also based on sensors embedded throughout the delivery chain, but they're measuring something a little different. And I'm going to describe these two in a little bit more detail. So let's talk about sensors. Conviva, we deal a lot in sensors. We have billions of sensors deployed in client applications for hundreds of video streamers. But of course, we look at things from a client side perspective. There are also server side implementations and approaches that are available in the market. And actually, it's really a combination of the two that you need in order to provide very granular reporting of latency throughout the delivery chain. The benefit of embedding sensors and agents is that it enables production scale 24/7 monitoring and alerting. And the main kind of mechanism by which these sensors and agents work is that they listen for and they collect various metadata attributes associated with the video chunks. So if we take the two most common video delivery protocols, Dash and HLS, both of them have various different metadata attributes in the manifest and in the chunks that describes that video file's journey down the delivery chain. And there's some examples of these metadata inputs that are provided here. Some of these are HLS specific, some of them are Dash specific, others are from other protocols. But essentially, as the video passes through these different points in the delivery chain, as it passes through the encoder, for example, passes through the packager, these attributes are stamped into the video, and then they're available for collection further downstream. So if you can look at the delta between the timestamp that the video went through the encoder versus the device time on the client that actually rendered that video, subtract the two, you've got a latency calculation between those 2 points. Right? So this is one of the techniques that's available. Another is fingerprinting. So in this scenario, this really sort of combines the probe and metadata approaches. So essentially how this works is that it tags unique frames in the video and the audio upstream, and then it looks for them downstream, right? And when it detects them, again, it will have a timestamp that the video was tagged versus a timestamp that the frame was detected downstream. It's a case of subtracting one from the other. So this can be deployed at really any monitoring point where a probe can be placed. It's codec and format agnostic, which is always beneficial. Very accurate. The challenge, though, is that whilst there's a sort of an attempt to make the process lightweight, it actually still requires quite a lot of resource for the process to be performed for that tagging and for the recognition, and also for the calculation of a metric on the back end. The other challenge with the fingerprinting approach is it doesn't work well for static content or for slates, right? If it's a talking head and there's really no difference at all in the video frames, then you're going to have, it's very difficult to identify a unique frame in that scenario. So it has some benefits, but it also doesn't work in every scenario. So let's talk a little bit about optimization. So what are some of the steps available to reduce latency? There's actually quite a lot, as we sort of covered earlier. There's quite a few. There's a huge amount that can introduce latency into the delivery chain. But as a result of that, there's a lot of levers you can pull. There's a lot of dials you can turn to try and tune for it. So on this page is no less than 16 different points of potential optimization related to video streaming. Some of this can include things like the switching to server-side ad insertion versus client-side. It can be things like optimizing your encoding settings, reducing the bit rates or the number of different bit rates in your profile, or reducing the segment size in your packaging. There's various network side levers that can be pulled. So things like quality of service policies and prioritizing certain traffic types over others. This can be an ISP level policy, or this can even be router level or defined in the home. There are optimizations that can be made on the end client. So parallel processing is a good example of that. So enabling you to decode and decrypt the video more efficiently, and hence reduce the rendering latency. So much as I'd love to go into the detail on all of these, we have a relatively short window for this slot today, but I'm happy to speak to any of these offline for anyone that wants to follow up with me afterwards. I do want to look towards the future for a moment and just talk about some of the emerging technologies that are aiming to reduce latency. Because, as I said, even at this point, right, with traditional streaming technologies, you can sort of pull all these levers and turn all these dials, but so there are some fundamental limitations in it that mean getting it below 10 seconds can be challenging, right? Certainly getting it below 5 seconds with traditional protocols it's going to be an uphill struggle. So there's two kind of key technologies that I want to call out here, focused on low latency. So there are some dedicated low latency protocols which have emerged in the last few years. So HLS and Dash, those were the two kind of most dominant delivery protocols I talked about. There are now low latency variations on those. Apple released theirs, I think 3 years ago. I think Dash, it was about 4 years ago. HESP is a more recent introduction. So there have been attempts to bring out technology focused on bringing this down to sort of, in the case of low latency HLS, it's sort of 3 to 7 seconds. In the case of low latency Dash, it's about 2 to 5. And HESP tries to bring it down below about 3 seconds. So it's certainly a big improvement on the traditional technologies, but there's always a lag in terms of the adoption, and obviously the client side support for these new protocols when they're released. Another technology that is quite interesting, and I've kind of dubbed this back to the future because it's blending a little bit of the old world with the new world, and that is multicast ABR. So multicast is actually a very old, very traditional mechanism for delivering video over networks. It's essentially how traditional digital broadcast, terrestrial cable networks, satellite, they've all used multicast in one form or another. And the benefit there is it's scalable, right? Everybody sees the same thing at the same time. You don't have to deal with the scalability issues of unicast and having a unique connection for every end client. But the challenge with that is it doesn't adapt to, traditional multicast doesn't adapt to the sort of network fluctuations that you have in public internet. And so combining ABR, adaptive bitrate technology, with multicast is ideally, gives you the best of both worlds, and brings latency down to something that's much more closely aligned with traditional broadcast. It's also just much more efficient, much more scalable, greener. There are all sorts of benefits to this technology, but again, there's a lag, right, between the technology becoming available and its adoption and its deployment in various different environments. But this is very topical. So actually,
sorry to jump in, Will, but we have to move to the next speaker very soon. So if you can wrap
that's
up
fine. This
quickly,
is the
that would
last
be
slide.
great. Okay,
Yeah,
thanks.
last slide. So yeah, just very topical. On Friday, BT Group in the UK, the largest ISP in the UK, actually unveiled a new technology that was designed to be, more reliable, more sustainable, focused on delivering live content over the internet. And one of the benefits to this should be low latency. So they're calling it multicast assisted unicast delivery, which essentially is the multicast ABR mechanism. And there's a number of the major UK broadcasters, including the BBC, that are going to be evaluating this in the near future. So it is a hot topic, but even in the space of the last few days, we're seeing major advancements and new technologies being announced and launched. So that is me. If you have any questions, feel free to reach out to me. I'm very easy to find. I'm will@conviva.com. Again, thank you very much for inviting me to be a speaker, and thank you for your time.
Thank you very much, Will. There is a question in the Q&A. We don't have time to do that live, but please answer it in the tool if you can. So we'll jump straight to our next speaker, who is Varun Singh. He's the Chief Product and Technology Officer at Daily, and take it away.
Hi, everyone. Thanks, Bjorn, for inviting me. Hopefully you all can hear me.
We can hear you, and we can see your slides.
All right, that's awesome. So very quickly, change of topics. I know, the talk is about latencies, and I was looking at redoing a talk from my past about latencies, but I decided that I'll take a different route this time. We know ML and Gen AI has been the talk of town for the last year. ChatGPT just did complete a year. So I thought we would look at things, this new technology, and see, how far we can take it where it is today. So a little bit about me. I started working with WebRTC 15, 20 years ago when it was still not WebRTC. Worked at the low levels of RTP, RTCP. Built a company called CallStats, which did latency measurements for WebRTC, and most recently, 2 years ago, I joined Daily, which is a WebRTC provider. And in the last year, we've been adding AI toolkits to help developers build AI products multimodally, so voice and video into their AI products. But what I think has changed dramatically in the last 10 years is that with every passing 5 years, we've seen an inflection point in AI. So in 2013, there were neural networks for natural language processing, which is kind of the backbone of the multimodal part of Gen AI today. Then we got the transformers in 2016.
in the meantime, we had the Alexas and the Siris invade our homes. So we've already been talking to like some kind of AI at home for a bit. But in the last year, large language models became more widely used with the proliferation of ChatGPT and other computing technologies from other folks. So ChatGPT and friends, like how does, mostly we don't think about latency in these cases, partly because the technology, the earlier versions of GPTs were over REST interface. People didn't really think about it. People who were building on top of GPT were thinking about latencies, but they were not front and center. In the last year, ChatGPT became accessible. Every one of us has an account with ChatGPT or similar and is chatting with them. The chat interface, in some sense, has a little bit more leeway. We know the GPTs are fast enough that we can have a conversation with them. But there are user experience toolkits available, by just showing like a beach ball or an hourglass. We know that something's happening behind the scenes, and it's not my computer which is running slowly. And this is anyway running on the cloud, so it's not my end anyway. So we text to the AI engine. The AI engine responds with response, mostly text, and we wait for the response, and we're kind of happy with the latencies that we see so far. Typically, what we've seen is this is either WebSockets or web transport or some kind of HTTP, HTTP 2, 3. People haven't really been optimizing all that much in that field, but it's something that we can look into. But when we look at multimodal, typically what we're thinking about is, voice or video. You're capturing my voice and camera, sending it to the AI engine. The AI engine does something to it and sends a response to it. And we're seeing more and more, just like we've seen with Siri and Alexa, they talk back. So you talk to it and it sends a response. The big thing that we are seeing differently with compared to the conversational AI things that we have at home, like the Siris and such, is that they were very interrogatory. Like the most common example that I just ask it the weather, like what's the weather? Is it going to rain? Like that's my the the context in which I interact with these things insofar. But what we are seeing people build now are more interesting. We've seen some demos from Google over the last few years where you called into a shop or into a restaurant, try to make a reservation, and that whole conversation with the reservation bot was actually not a human, but was a bot mimicking human speech. So the ums and the ahs and all the things that we see with human speech were being mimicked by the bot. And now most of that technology has come with the LLMs. You can take an LLM, you can talk to it over text, and it'll respond. You already have the other pieces, if you want to think about it, is that you have a text to speech, you have a speech to text. So there's nothing that forbids us from building something like this. So quickly jumping in, this may feel like an ad, but basically what we did over the last month is build an app, which is, we are an API company, so we're not really into building apps. But what we wanted to do as a way to measure latencies and see like how useful an app would be is we build something like talk to Santa Cat, call the app. The app is a bot on the other side. It speaks back to you. What was challenging for us here was, it's mainly aimed at 8-year-olds, and 8-year-olds, when something like this talks to them, they can't organize their thoughts fast enough. And we had to work with human latencies and cognition a little bit to kind of like figure out how to make this app work. We definitely recommend you all to use it and give us feedback. None of the audio or the video is stored, so it's all like peer-to-peer. Doesn't really actually store any of it, but we do capture latencies. We try to see if the bot was interrupted, the bot spoke over a human, so we do collect some statistics around that, mainly to improve the latency. But we would love for you to all try it out and give us feedback so that we can kind of try to figure out where the latencies are and what we can do. So very quickly, like what does it do? You have human input, live processing at the client. the client talks to a server, the server converts the speech to text, or image to text, or image to image, depending on what we're trying to do. The text is fed into an LLM. The LLM responds. In this case, you talk to Santa Cat. The cat basically listens to you. You may ask about the North Pole. You may ask about Santa. You may ask for a gift. It tries to conjure up a response, sends back that response. We convert that response from the LLM back to speech and send it back. Just to be clear, none of the data that you're speaking to or coming back is used for training or anything. It's not even recorded. So basically, if you think about it, you could build this over WebSocket, WebTransport, WebRTC. We chose WebRTC because it was the best option. With WebSockets, you have the issue with, you can stream packets, but you have to handle all the audio chunking, maybe line blocking. WebRTC, we didn't really have to think about this. We just treat both sides of audio, text to speech, and the human voice as standard audio, 20 milliseconds chunks, and we send it back. But there are things to consider here. Voice activity detection. So when you stop speaking as into the client, then the bot needs to start to convert that to speech to text. It needs to send a response back. So you don't want it to speak over the human, so you have to kind of figure out how the human stops speaking, for example. Then audio packetization, generally 20 milliseconds is used. Is that the best option, especially when we already know the text that is going to be converted from text to speech? And then there are things like redundancies, like the FEC and the NACs. And there's a lot of body of work that Siri did. Siri uses MPTCP, Alexa uses UDP with and a lot of folks today are using WebSocket. So there's a lot of data out there, like on how to build like redundancy into this. But again, like something to consider if you're building. As I said, latency stack up. So you have the speech to text. I'm speaking right now. Someone's listening. They need to respond. When do you actually know the speech is done so that you can convert it to text? Then the text needs to fed into an LLM. LLM has to respond, which is like which is the known latency that we know from ChatGPT. So you can easily mimic it and you can see how it would behave. So you can simulate it. And then there's a text to speech, which again, like what I'm going to come to is like speech to text and text to speech parts. All those seem easy. They're not kind of that easy because we hem and haw, we interrupt each other. And sometimes when we speak, spoken English spoken languages are different from written languages. So how you say a question when you write is completely different than when you speak. We use a lot of intonation sometimes to suggest that this fragment of a sentence or that sentence is a question versus a statement. So very quickly, in terms of latencies, and kind of depends on what kind of app you're building, but basically you want to convert speech to text. With WebRTC, you're getting the speech in real time, so there's nothing that stops you from converting speech to text. So if you have voice activity detection, very short one would give you can parse out each word, because if it's like 10 milliseconds, 5 milliseconds, like what kind of threshold you want to put between spaces of audio fragments, you can figure that out. The other one is punctuation. So if the question mark, comma, detect that there are longer pauses. And then there's a talk spurt, because at some point, if I'm talking to a bot, I will stop talking, and then you can convert all of that into from speech to text. The advantage of waiting for the talk spurt is that you have the most context. When you give it to the speech to text engine, it has a lot more to like go on. It can do a single pass, it can do multi-pass. We're talking about tens of seconds, no more of a talk spurt, 5 to 10 seconds. So very quickly, it can gather context, give you a very robust response to convert the speech to text. Kind of depends on like how much accuracy. So like the main gain here is like what type of accuracy you're looking to get from the system, and that contributes to your latency. Then you have the text fed to LLM. You can stream in some cases. You can say this is going to be multi-part. So as I'm getting my text from the speech engine, I can like feed it. When you're done, you can say final. It will finalize it and then say, okay, you sent, don't have to send a full text block, for example. So the APIs have become much better in this case. So you can stream it to the LLM, when you say final, it'll finalize it. Maybe actually responds faster in that case and sends it back. And the last bit, which is like then text to speech, again, the question, you have this whole text, it needs to be spread out. It should, if you do it sentence by sentence, then you have to do it fast enough that these sentences don't sound like disparate sentences, because there's a big pause. The human will start to talk in between those sentences. And if you do word by word, which will give you like the smoothest, you may miss some context because, as I said before, spoken words are not exactly written, so intonation and such would be lost. So again, like a lot of interesting things. Again, latency stack up in here, depending on what choices you use. So just reiterating, you have human input, you do speech to text or image to text, send it to LLM responds, you get back text, you convert that into audio and video, and then you send that, or you stream that audio and video back to the user. So lastly, I would, it's in the App Store. I would encourage you folks to give it a try. And if you find issues, if you're able to, co-opt the LLM in some way, anything you do and you think that the app shouldn't be doing, feel free to write it to me, and I would share it with our engineering team. The whole purpose of this is to make it into a library so that more people can build these things. But we want to make sure that we build some kind of safeguards and kind of best experience in this case for folks to kind of find their way into building the next generation of apps, which may actually include audio and video as first-class citizens as a user interface. So that's the end of my talk. Open to questions.
Thank you very much, Varun. It's very interesting stuff. We're back on time if we jump straight to the next speaker now. So please, we'll do the Q&A by text. If there are questions.
Thank you.
Thank you very much, Varun. Our next speaker is David Tubes from Cloudflare, and looks like you're ready. So please take over the screen sharing and go ahead.
Fantastic. Let me know when you can see my screen. We good?
I can see a screen now. I can hear you loud and clear. So
perfect. I love. All right, I'll make the participants go away. Awesome. So good morning, good afternoon, good night, wherever you are. My name is Tubes. I am a principal product manager at Cloudflare. And today we're going to be talking about CDNs and how they make you fast. We've had a lot of really great talks today about things that depend on latency to be successful. And one of the things that I want to talk about is less about, how CDNs, less about, the things that CDNs are doing to, invest in latency, because that's kind of like an inherent, that's kind of an inherent given. What I want to spend our time doing is talking about a little bit about why we care about latency from an applications perspective, metrics, what a CDN does, and how that helps you. So you can see that all on my agenda here. So without further ado, let's get straight into it. Why should anybody care about latency? We all want to be fast. At the end of the day, latency has a direct correlation to revenue. And, if you're just, a guy or a person just, sitting around waiting for a web page to load, you might just navigate away from that web page. And that anecdotal evidence suggests that, you want a web page to be fast. But actually, there are a lot of studies that were done by a lot of important companies that suggest that latency has a direct correlation to revenue, and the slower you are, the less money you make. Even true for stockbrokers who lose $4 million per millisecond of latency. So for those of you playing the home game, the blink of an eye is about 200 milliseconds. So if you blink your eye, you've just lost stockbrokers $800 million, which, is obviously not true, but, what if we could? The summary here is, if you care about revenue on the internet, if you want to make money, if you want to be successful, you have to be fast. There is no way around that. And when we talk about fast, fast means different things to different people. You know, you heard Varun talk about, you know, AI latency and what that means to him. You've heard Will talk about, you know, what it means to him as well. A lot of great speakers are talking about how latency impacts their applications, and it all means different things to different people. Generally, for web-based content, we look at a statistic called largest contentful paint, which is how long it takes the browser to render a page. API-driven scenarios are probably going to be response-driven. So HTTP, W3C, you should be familiar with these. You know, video chat, RTC, you're going to look at SIP latency. You know, Varun and folks gave a really good breakdown of, you know, the web RTC latencies and what matters there. Gaming, you know, we had the friends from NVIDIA give a really good talk about that. RTT and all of that stuff is super driven is the metric that drives a lot of that. So, you know, based on your scenario, you care about different things. But we all kind of look at similar measurements, especially when we start talking about percentiles. Generally 90th percentile, at least from a CDN and networking standpoint, is where we start to, you know, look. And the reason is that if you go any higher on the internet, you're going to see lots of hairpins. You're going to see lots of one-off networking scenarios that cause people to be slower. And so LCP in response, 90th percentile is a good starting point and gets your data consistent that if you can, you know, start optimizing that, then maybe go higher. But, you know, 90th percentile is at least where, you know, us at Cloudflare start to think about that stuff. But the higher you can go, the better. Before we go in, I just want to be very clear that this is not a sales pitch. I am not trying to sell you Cloudflare. And you know, if you want someone to sell you Cloudflare, go find an account executive, go to a website. There's plenty of people. If you want to buy Cloudflare, you can go talk to. My job is not to tell you to buy Cloudflare. My job is to say that a CDN is critical for you to be successful. And so if you buy Cloudflare, great, you know, more money for me. But if you don't, you should be choosing a CDN, and you should be choosing a network to partner with that helps deliver a good performance to your users. And you need a CDN to do that. CDNs at their base, they stand for Content Delivery Network. Essentially what we do is we serve cached content to users. So if, you know, you have a website and you've got a whole bunch of stuff that needs to load, you know, maybe you just go tell a CDN, hey, you know, instead of me serving this directly from my application or origin, you can serve it on my behalf once I serve it to one person. And that means that everybody afterwards gets a really good performance because my data is already on your network. And that's one thing that CDNs do. But as you'll see, CDNs do a lot of things to help improve network performance. And a lot of these things are things that are very hard to do for application owners at scale. You know, you could, if you wanted to, go buy a whole bunch of bandwidth and a whole bunch of data centers and deploy there. You could deploy all this to the cloud if you wanted to. You could run a CDN out of Google or Amazon or Azure or whomever, but that's a lot of work. And it's a lot of effort. And, you know, as an application developer, like Varun shouldn't have to worry about how many points of presence he's deployed to for his application to be fast. He should just be able to go talk to his CDN and say, hey, serve my application for me. And then it just does that. And, you know, Will's diagram about the content distribution network, that I was really glad that he didn't dig into that because he would have stolen my thunder a little bit. Our job is to be as ingrained into the internet as possible so that we can serve content directly to users as fast as possible. And sometimes that's bundled with fun extra features like security. You can get a WAF, or you can get DDoS, or you can get zero trust, or you could even develop, or you could even deploy certain functions in tiny little bits of code called serverless computing on a CDN and sort of democratize your workload across a purpose-built network whose job it is to be everywhere and as fast as possible. So it's basically kind of performance built in. And if you're watching this, then this talk should look really familiar because I sort of gave this talk last year, right? Like CDNs, you know, the world hasn't really changed that much, but actually the world has changed. So what's different from, you know, today versus a year ago, the last time I gave this talk? And there's a couple things. So the first thing is that the metrics that we look at for web applications have changed. So it used to be we looked at time to first byte and we looked at response, which are good metrics. And, I talked about in the metric slide and talked about API usage, how response is a really good metric. But for web applications, maybe not so much. So we move on to largest contentful paint. We got a blog about that. Another thing is that attacks on the internet became more complex. People are moving to the internet. You can see there's a 23% growth in internet traffic, which is awesome. But it means that attackers and people who want to do bad things are trying to do bad things in more complex ways, which is cool because we get to write fun blogs about it, but it's an existential threat to applications on the internet and things that application owners like yourselves need to consider when you start, building an application and trying to be fast. And finally, the last cool little tidbit is that more and more people are moving towards APIs, right? It's not just, hey, like you give me content, you host a website and you serve content to people. There's a lot of API traffic that happens under the covers, and that increase is, pretty uniform across the board, but mostly happening kind of the finance space. So all of these trends mean that CDNs are really important, and they help you be fast. But how do they help you be fast? So let's talk about it. The first way we talked about before, caching. Pretty straightforward. We host content so that we cache your content so that you don't have to. If you have one application that's hosted in, let's say, Seattle, where I live, then, if a user in Seattle is trying to get your stuff, then great, it's nice and fast and easy. But if you're, say, Bjorn, and you live in Europe and you're trying to get content hosted in Seattle, that's a pretty long way away. But if the CDN has a node or has a data center in Europe where that content is cached, then Bjorn can just go there and you can just grab that content, and he doesn't have to go all the way back to Seattle. That's because uncached latency is a problem, right? The more you have to traverse the internet, the slower you're going to be. And it's not just the physical distance, right? There are, security protocols like TLS, which have a three-way handshake, which means if you are going from Europe to Seattle, you're not just doing that once, you're doing that at a minimum of 3 times, which means that your application is going to be a lot slower. At the end of the day, network latency is multiplicative. You have to make that trip, but the question is, how many trips do you have to make? So there's a couple of options. You can either shorten the trip that you have to take, which is the value that CDNs provide, or you can reduce the number of times that you have to take that trip. And there are tools that a lot of great security providers have provided, but if you're an application owner, you might have to build those yourselves. Not the case if you use a CDN. So back to caching. Caching keeps users hitting the same endpoints without needing to go back and forth. So it improves your latency, it improves your LCP, it improves the things from a static resource perspective that matter to you. But, let's say that you're building a network to host video streaming. God, I can't believe, I wonder what kind of network would be like that. And you don't have any dynamic content. Or if you have dynamic, or if you don't have any static content, or if you have static content, a lot of people are accessing that static content at once. The next piece of value is around what's called shortest path routing. So on the internet, the fastest path is the straightest path. The shortest distance between 2 points is a straight line. So obviously you want your path to be as straight as possible. If you think about the internet, it doesn't necessarily optimize for latency. We've talked about this, and a couple of other people have talked about this. The internet optimizes for packet delivery. It optimizes for best possible availability, not best possible performance. And what I mean by that is you think of the internet like this, right? We think of the internet as the abstract of a user going to a website or a user going to a thing, right? And whether that thing is hosting your ATM card or your banking application or a Zoom call or a game or an AI application or whatever, you can host any of these things. But it actually kind of looks like this, right? Like there is a lot of steps between your device and the content that you access. And Cloudflare could be in the path there. But that's actually not a really good way of thinking about it. Actually, the internet is so many different possible paths interleaved together that it doesn't look like a series of straight lines. It looks like this crazy mesh, and it's really complicated. And routing on the internet is, as you've probably heard and will hear going forward, is really complicated and difficult. And this is something that as an internet hosted application, you do need to think about, because as we're talking about latency and we're talking about reducing network latency, the best way to reduce network latency is to reduce the amount of distance between your user and your stuff. So CDNs can do that by being a very good source of ingress for your application. If you ingress if your users ingress to your application close to them, then they don't have to traverse the public internet as much. But also, a lot of CDNs offer latency optimizations on the middle mile that will dynamically route traffic over the internet. So basically, a lot of CDNs, they're ingrained with, the big clouds and lots of ISPs and lots of different peerings, so that they can figure out the best path from where your user comes in to where their content is hosted. And finding that path is very important to reduce latency. You can reduce latency by up to 30% if you do this stuff. And it's a lot of networking, and it's a lot of routing, and it's complicated. And yeah, you could do it yourself. There's none of this stuff that is unique to CDNs, but this is the stuff that CDNs build their business on and make it valuable, so that you can just, press a button and get it set up for you. The second value is with TLS negotiation. So before we talked about shortening the distance between a user and your application, and that really, really matters when you talk about TLS negotiation, because TLS negotiation requires a whole bunch of handshakes back and forth. Your user has to say, hey, I'm trying to get my stuff and I'm authorized to do it. And then the application has to say, yes, you are authorized to do it. You can go send data now. And then your user will say, okay, I'm going to go send data now. And that's a three-way handshake, and that takes a really long time. From Bjorn to Seattle is probably about 120 milliseconds. So if Bjorn has to do a three-way handshake authenticating in Seattle, he's spending 360 milliseconds over a blink and eye and a half of time simply talking to the server and validating that he is authenticated to send traffic there. That's a really long time, and that adds up. So there's two ways to shorten this, which is getting closer to the users, right? The shorter round trips means the less time, but also things like session resumption support, meaning that you don't have to authenticate as much, meaning that these three-way handshakes happen less. All of this stuff is very valuable and will help you be faster. And finally, how we get there, how we get closer is with peering and network operations, right? Like, all of this stuff requires time and money, and networking especially requires a lot of time, because debugging this stuff, talking with network providers, making sure that everything runs is a business in itself. And you can build all that, right? Like, you could set up your own peering, you could set up your own NOC, but CDNs will do this for you, and you can use their services, which at the end of the day is going to save time and money. And also, it's going to save even more money for you in the long term, because if you have to set up all of these deals yourself, you're probably going to be paying a premium for it, but CDNs tend to get better deals on these harder to reach networks, which improve your performance even more. So the kind of summary here is all of this stuff that I talked about, none of it is unique, right? Like, none of it is special. TLS, session resumption, networking, getting close to users, all of this stuff is known and it's real problems, but all of that stuff is stuff that you have to build, right? Like, if you talk to, Dave Tott or Jason Livingood, and you ask them, what's the one thing that will fix this? Dave will jump up and down and say, cake. And Jason will say, L4S, AQM, give me that stuff. You can build that yourself. You can build the support for that into your application, and you should. But when we talk about getting the next level of performance and getting the next level of, what's that stuff that's going to impact and benefit my users, you can build that yourself, or you can pay a CDN to do that for you. And not only will you get the latest stuff like HTTP3, L4S, AQM, 0RTT, more security, you get closer to your users and you add better performance to your network simply by adding that extra hop that has all of the network performance and latency benefits that we're talking about built in from the jump. So it's a really easy way to get access to a lot of the tools that we're building simply by just pressing a button and getting configured. And you know, a lot of CDNs often have free plans that allow you to get set up and going and kind of running from jump. So there's a lot of different ways to do this stuff. And, you know, in terms of implementing this, you can do it yourself. There's nobody saying you can't. And, you know, but you could either invest your money and time and distract from your application, or you can get a CDN to do it for you and then focus on the things that really matter, like the next level of performance, such as optimizing your application and making it faster from there. So that's all I got. I think we're under time. So if we got some questions, I'm happy to take them.
Thank you very much, Tubes. Yes, there is a question here. It's is the density of CDN required to achieve good latency a function of distance to last mile or density of connections in a given area, or both?
Is the density of CDN required to achieve a function of distance to
I
last
guess
mile? So yeah, the way that I would think about this is generally, so there's two ways of thinking about it, right? So like CDNs offer kind of a forward and a reverse proxy. For the reverse proxy, for the end user, the last mile is generally going to be the thing that's going to drive the performance. But when you think about connections from, you know, a CDN to your origin, density of connection starts to matter. So the answer to your question is it really depends on whether you're looking at the last mile or the middle mile, but density matters on the middle mile, but distance matters on the last mile. I hope that answers your question.
Cool. All right. Thank you very much, David. And we will move on to the next speaker now. So our next speaker is William Hawkins and he's a professor at the University of Cincinnati, prolific open source contributor and organizer of the RPM community. So Will, please take it away. I'll let you know when the slides are up. See, they seem to be working. And you're muted still.
Got it.
There we go.
Yes,
good. Now I can hear you.
Yeah. Thank you all very much. So as Tube said, he was not trying to sell you something, but what I am trying to do today is in fact sell you something. So I am trying to sell you on the fact that it does take a village to work through some of these latency issues, in particular those caused by buffer bloat, and that we are trying to foster that community in order to bring researchers and interested parties together to work through some of these issues. So this is a little bit confusing to me because one of these things is not like the other. So these are some of the presenters who are going to be speaking or who have already spoken. And then there's me. So I will let you choose which one of these things is not like the other. But I'm pretty sure you already know who that is. So what am I going to talk to you today about? I'm going to try to answer these questions. Why is there a need for the community? What has our community done for this process? What resources have we made available to the community? And what would we like to offer in the future? How you can get involved? And if there's any questions, I'd love to be able to answer those. So fundamentally, I don't think it should be too controversial to say that we're all smarter as a group than we are as individuals. And I think that in networking or in computer science, this is particularly the case because of the layered nature of everything that we work on, whether it's theoretical computer science or writing an operating system, or where these layer models come in explicitly in networking. When we don't know everything about a particular layer, but yet that could still cause us a problem, we need expertise in all those different areas. And so one of the things that the community that we're trying to build is people from all of these different layers. We are trying to get together people who work on applications, people who work on transport protocols, people who work on internet protocols, people who work at the hardware, the physical layer. We want all of those people to come together into one place so that we can really have these fruitful discussions about how some of these different layers affect each other in terms of how we can solve the latency issue, lower latency for customers or users. So what has this particular community done, and why do we want you to join it? So in particular, this community started around the draft responsiveness under working conditions that is currently in standardization at the Internet Engineering Task Force. And in particular, we wanted to bring people together who could help us iterate on this protocol. Now, I don't want to steal Stuart's thunder. He will be talking, I think, tomorrow, and he will give a complete overview about responsiveness under working conditions. But briefly, what is responsiveness under working conditions? Well, it's a methodology that we've put together whose sole goal is to help users understand the latency of their internet connection while in a form or as it is being used as they would normally use it, let's say. So for instance, we are not trying to develop something that measures unloaded latency. We are not trying to measure something that, or we're not trying to develop a methodology that measures latency under the perfect network conditions. What we're trying to build is a methodology that will let users discover their latency in a meaningful way, as if they were using the connection on a day-to-day basis. Most people, we know, they are Zooming and they are streaming Netflix at the same time as they're watching YouTube. I don't know how they're watching two videos at the same time, but they are. And so that's what the goal of responsiveness under working conditions is. And again, I don't want to take away from what Stuart will talk about tomorrow, so I will leave it there. But I'm more than happy to take questions about that. So that was the impetus for building this community. But we've since expanded, and some of the other things that we've done are to actually go and implement open source versions of this methodology. And we've been updating these implementations as the methodology has advanced through the standardization process, and we have gotten feedback from members of the community. So what do we have right now? We have a full server implementation. Right now, we have two of them, in fact. One of them is written in Swift, and the other is written in Go. Then on top of that, we also have configurations that you can use if you are serving or you want to participate or host a testing endpoint, and you're already familiar with using Apache or Nginx. We have configurations for that as well. So the methodology that we've proposed has both a client and server. And one of the things that we've done here as an open source community is to develop these server implementations. But we've gone a little further than that. We've also done a full client implementation, and this client is written in Go, which means that it is usable on any of the platforms where Go is fundamentally usable. And what we think is really neat about this Go implementation is that there are various protocol extensions that are built into it. Responsiveness under working conditions is going to be standardized in the IETF, but we're always tweaking. We're always trying to understand how can we extend that methodology to other things. And so what we do is this is a good test bed for us to say, how does this actually work if we tried to implement this as a test? It also offers extended OS level statistics, which are gathered while your responsiveness under working conditions is being measured. There's also great graphical representations of the results, which show you how your network connection is being used during the test. I'll show those in just a second. Also, we have the ability to display quality attenuation statistics, which Bjorn is very familiar with, I'm sure. And also, we have a integration with OpenWRT. So if you would like to add this client to an OpenWRT installation, you are more than welcome to do that. So before I go on, I just wanted to show you how something like this would work. So I've got a server running on the cloud right now, and it is the Go implementation of the server. And now I also have a version, or I also have a client running here on my Linux machine. And I just ran this test so that the demo daemons don't get me, but let's try it again. And it's as simple as doing this. What will happen is I'm specifying here that I want my test endpoint to be this host in the cloud that I have built and am running. And it will do two separate tests. It will test for your responsiveness under working conditions on the download direction and the responsiveness under working conditions on the upload direction. And then at the end, it will massage those two scores together and present you with a final RPM score. So we'll wait here and it will finish momentarily. Awesome. All right. So the demo daemons did get me, but such are things. So again, the client works on any operating system where Go can compile source code for. And what I mentioned earlier was we've got these extra graphs that will come out. And this is one of the graphs that you might get presented when you are running the client and generating these extra graphical, this extra graphical information. We think this is really cool because what responsiveness under working conditions, the methodology does is try to saturate your connection before it measures your responsiveness. So what you can see here is each of these different colors is a different stream of data that is a different TCP connection open to the server. And what we think is really cool is you can sort of see how as you add more over time that there's still fairness there. And that's really quite cool, actually, to see this graphically presented. So, of course, that's not the only graph that you can get. But again, I don't want to bog us down into the details here. So more than happy to come back to that if you have any questions. All right, so what else have we done? That's just one of those things. Well, the other thing that, that one of our members have done, in particular, Felix has done a great job on this. He has actually implemented the responsiveness under working conditions methodology into LibreSpeed. So now if you are interested in running a LibreSpeed node, you can do that and offer your clients the ability in any of the 4 major browsers to measure their responsiveness under working conditions. All of this, again, is open source, and we will have the links at the end. And then as Bjorn shares out the slides, that'll be also available there as well. So that's pretty cool. The other thing that we're really trying to focus on is to be good open source stewards and to take our understanding that we've developed about where buffer bloat and where latency can infect a connection and try to contribute back to open source projects so that they are, so that their networking tools that are built into some of these things are more, follow more of the best practices. So we've made several contributions to the Go runtime. We've made several contributions to the Apache traffic server, and we're continuing to do that. That's one of our goals, is to take the knowledge that we build in our discussions with one another and contribute back to the community. We also have some other available resources, and this is thanks to another one of the presenters, Bob McMahon from Broadcom. He has generously donated to the community some testbed equipment. We've got 2 Raspberry Pis that are connected over a gigabit Ethernet switch. And these are running relatively recent versions of the Linux kernel with BBR version 2 and TCP prog congestion control algorithms already built in. And I believe Neil Cardwell will be talking about BBR and all of the work that he's done on that tomorrow. So more to come for there. But if you're interested in testing your application on something where these congestion control protocols are available, then we would love to be able to give you access to this testbed. And another one of the presenters is from Tailscale. So I can't skip over how awesome Tailscale is, and we can give you access to these resources directly over Tailscale. So that is pretty much where I want to end up with my call to action for you. Everything that we have and everything that I've discussed today in this sales pitch is available on GitHub at github.com/network quality. And in particular, we have open meetings every Thursday at 11:30 a.m. Eastern time. That's 4:30 GMT. And we would love to have your participation and for you to join us. As I said at the beginning, the more people that we have together talking about this issue, the more people at different levels of different areas of expertise, different networking layers, we can really have some good discussions. And I think the work that our open source community has done to date shows just how powerful the community can be when we come together. So I think I will, I'm happy to take any questions.
Thank you, Will. That's great. I do not see any questions at the moment.
Okay.
I want to add to your thing about the meetings on Thursdays, because
Yes,
I've been attending those as well, and I think they're a great place to meet people who are like-minded, working on this topic, and it's possible to like drop in and check it out. You don't have to
Yep.
commit to every week.
No.
If you want.
Yeah, there's no
It's,
commitment necessary here. You know, we would love to have your expertise as often or as unoften as you can make it. We're just generally glad to have as many people as we can to contribute, because like I said, I think we've made some great progress just by putting our heads together and thinking about these things. So I would love to help you get involved if you're interested. So thanks for having me.
Cool. Thank you very much, Will. All right. So we will move to the final speaker for today, actually, and that is Damien Sturkers from Broad Peak. And yeah, looks like Damien is ready.
I
so
am.
Please take it away, Damien.
All right. Thank you very much. Hi, everyone. So last session of the day, let me put this.
I'll
There
let
we
you know
go.
when we can see the slides and everything.
Yeah.
Yes, and it looks to be working now. And we can also
All right.
hear you well and see you well.
Okay, excellent, excellent. So last session of the day, that will be about latency, specifically in video streaming. So what is the topic? This is typically what we want to avoid. So what kind of latency are we talking about? Basically, we don't want to be the last one. So there's of course the use case of the noisy neighbor that will shout for a goal in his living room while you're having a product with more latency and you're still watching the action. So that's a traditional one. I don't know if it's that often that you get to that situation, but the truth is that it's getting worse with the arrival of social media. So very often people get notified of things, so that can become more of a problem nowadays. So where does latency come from when we're talking about streaming video? As I was saying, we don't want to be worse than the reference, and the reference in video is typically the broadcast. The broadcast is pretty fast, because basically you're pushing the content. You're not relying on people, making connection and so on. And let's say that end-to-end, from the capture to the display on the screen, you get something like 5 seconds of delay, right? So part of it is coming from the video encoding, great part of it. And the delivery in broadcast is pretty fast. Now, more and more people are using streaming technology nowadays to access their video content. And probably a lot of them have noticed that, it takes a longer time to get to the screen. We've started with something like, I would say 40 seconds. And you see here that part of it is coming from the packaging. I'll get back more in details about what this is. And a wider chunk on the player buffer. So basically, in front of a streaming player, you will have a much larger buffer, and will account for most of the latency that you get in streaming compared to broadcast. So actually, 40 seconds might be a bit too much. Today, people tend to optimize a bit, and I'd say that for someone, a system that is pretty aware of latency, 25 seconds will be more of a standard latency. You see that it has a link with the size of the segment of the video that you're transporting. So basically, every piece of video that you're sending is encapsulated into a wider entity that is called the segment, and it's not really a good idea to have a too long segment. Same thing, we'll get back. I'll explain why it's the case. But so typically today, I would say the starting point for most people will be that they're using 2-second segment, which is not too far from being optimized. And you see that there are these two sources of latency at the packaging layer and the buffering. Right, so you see here in my chain, the first level is the encoding. It's a big chunk of the latency we're seeing. But the thing with the encoder is you can definitely reduce the latency, and this is what is done typically in contribution applications where you want the content to come fast. But there's always a trade-off with encoding, between quality, latency, and bitrate. So if you reduce the latency, it's at the expense of the efficiency, meaning that you will typically either lower the quality of your video, or you'll need to have a higher bitrate for the same quality. Right, and this is what we've seen, for example, with the codecs. So we're using H.264 with a certain level of complexity. It takes some time to do the encoding. When going to H.265, we've increased the latency, but improving the efficiency, and that makes sense for video because video is pretty wide, and this has as a consequence to make the infrastructure more efficient and less expensive, which is quite important. And the last thing is that, encoding is not very different between broadcast or the reference and streaming. So it's not really where we can make a difference. So all that to say that there's usually not much to gain on the encoding side. Now, regarding the distribution, there you'll find your 20 seconds. And you can split that, as I was saying, most of it will be on the buffer and part on the packager. So starting with the buffer, how come we get so big a buffer when we're doing streaming, which wasn't the case for broadcast? Essentially because when you're doing streaming, you're relying on HTTP distribution, and by nature, HTTP distribution on the open internet is variable. Meaning that sometimes it's going to go fast, sometimes it's going to slow down, right? But your video player is going to consume the content always at the same pace, right? Which is basically 25 or 30 frames per second. So on one side, consumption is steady, but the way you're receiving your content can be variable. So this is why you need to have something in between to mitigate that, right? And this is exactly the role of a buffer, right, by definition. So, of course, the game is never to have a buffer that is too short, because if the delivery slows down and you get into this, right, where you see your packets are coming slower, then you're going to empty your buffer. It's a buffer starvation, and you're going to get this very annoying buffering that you see now and then in streaming. Right? This is really the game regarding the buffer, is to try to find the sweet spot, to reduce it the most you can, but it all depends on your network, so you cannot do it too much. Otherwise, you'll get some other problems. So you're going to decide the optimum level of the buffer. Now, what's interesting is there exist some technologies stream delivery more steady. So I'm giving you two examples here. One is to give some control to the server side. So this is a technology by which, typically when you're doing streaming, it's the client that will decide which layer, what speed, and all that. but somehow you can leave some of the decision to the server, and then the server will kind of trick the client to make it believe that he's received what he was asking for, but actually, you know, you can tweak a bit the way the delivery works. Now, another technology that radically resolves the problem is multicast ABR, because the principle of multicast ABR is whenever you get a lot of people trying to watch the same thing, and that's going to happen typically for a live event, what you're doing is you are encapsulating the streaming packets into one IP multicast stream. So it will be one for everyone, and here you can secure the delivery. So it's the same multicast IP multicast technology that you would have in IPTV, you know, if people are using IPTV. So basically, instead of having these bursts of packets, you will have a very smooth stream. And because it's only one stream for everyone, you know, it's what we can say, no impact on the network, right? It's one single stream rather than as many as people are streaming. So, so if you have a good network, if you have good optimization, then you can reduce your buffer and get a better latency, right? So when you're doing that, you see that, you know, the network buffer, you're going to shorten it to something between 10 to 15 seconds to maybe 2-3 seconds. And so you see here the delta with the broadcast, which remains the difference, is only 5 seconds difference, right? So it's already quite interesting. But again, you know, you can only do that if you've done something, you've created the condition on your network so that to allow to reduce that buffer on your player. And now there's, yeah, maybe a last comment on that, which is that it's quite important, you know, all this topic about constraint on the network, because what we see nowadays is that in streaming, live traffic is increasing, and it's going to become even more important than VOD, right? You know, streaming has started with VOD, with Netflix and so on, but that's because it's easier. But now more and more you see that very popular live events now are only streamed and not, you know, just broadcast through the legacy networks. That's the case, for example, for national championships of football in Italy, or we see that Prime Video has bought a lot of rights for Champions League in many different countries in Europe. So you see how it makes a difference is that when you have live streaming, it makes these peaks of traffic like that, right? Because VOD people will use it at different moments in time, right? Rather, whereas live, you'll have everybody trying to consume at the same time, right? So basically, the moment you constrain more your network, and it's going to be harder to reduce the buffer, is exactly the moment, you know, for this popular live event that you'll be willing to have low latency, right? Because on a movie, it's less important than on the live event. That's on the live event that you would like to have low latency, and it's the moment that is the hardest to get on the network, right? So you know, that's the first thing. Create the condition on your network so that you can afford to reduce the buffer even in this worst condition and any point in the network, right? And now if you want to go further and go less than this 5 seconds difference with the broadcast, there's another technology which is called chunking. That is the base format is called CMAF. So how does that help? You know, by default, if you're using the normal format, the funny thing is that it's called ABR or OTT streaming, but you know, like broadcast through IPs was a kind of streaming, but when we're doing OTT, it's more of a progressive download. So it's a progressive download of pieces of content, typically 2 seconds or 10 seconds at a time, but one after the other. So what will happen is that you get your live encoder producing the stream, and the stream, this segment needs to be totally ingested by the packager process that you find in the head, and before it can make it available downstream, right? So because the encoder is real time, it will take 2 seconds to get all this information, and only at this moment the player will be able to request that content. And same thing, the player will need some time to request the whole thing before it can display it to the decoder. So here it could be higher than real time, but typically the player in OTT will tend to get the highest layer possible. So very often it's at the limit of the real time, right? So here in this example, it's very schematic, right? Because there are other things that is happening in this small cloud here, but you're losing 4 seconds. So the idea of segmenting with CMAF is that you subdivide this 2-second segment into smaller pieces that are called chunks. So you do that at the level of the video, and this is where CMAC format is helping. And there's another technology, another format that has been existing for a while in HTTP that is called chunk transfer encoding. Exactly the same principle, but at the transport layer. So if you combine the two, you have the ability to make these smaller pieces. And if I'm taking the illustration that I was talking about 2 slides earlier, I'm going to get the beginning, the first chunk here, and the player will request this segment. And instead of having this system saying, no, I'm not ready, I don't have everything, it will say, well, I don't have everything, but let me get you what I got already, right? So as soon as it's getting something, it can transmit it to the player thanks to chunk transfer encoding, so at the HTTP layer. And same thing when the media decoder will need this segment, even when it's not completed yet, it can still use this CMAF chunk to be able to display something, right? So you see here, I've got 0.2 seconds, so 0.4 seconds in total instead of 4 seconds, exactly the same principle, but we've just divided the problem by 10, right? And because it's divided by 10, we consider that we don't have the problem anymore, right? So if you're doing that, you see that you can match the latency that you typically are getting in broadcast. So there's no fatality. It's possible to get the same level of latency both in broadcast and in streaming, even though this is not what we've experienced so far in streaming. Right. So that's the summary. The main thing, if you want to achieve latency in streaming, is to create the right condition on your network, so that you don't need that big buffer. Right, you can be more aggressive on the time that you're buffering in the player level. Be careful that sometimes lowering the buffer, that it works perfectly in the lab, of course. So you get the impression that you got a product that will do it. But when you put it in the real network, then you get the real network conditions, and they are tougher, and you see that it is no longer working. So lab is not enough. It's something to be tested directly on the real network. Be careful with the peaks of traffic of live. It creates really the worst condition possible on the network. And then only when you've reached that point, then it's interesting to here, as I was saying, you'll be a few seconds late compared to broadcast. And if you add CMAF format in your video streaming format, then you can match the latency of what we get on broadcast. So only good news. It's I guess streaming is more recent than broadcast, less experience. So they've started with more latency, but it's just a lack of maturity. There were some more higher priorities to deal with. But technically, there's everything to get a latency at the same level of broadcast. This being said, that's the end of my presentation, and I think that's the end of this session today as well. So back to you, Bjorn.
Thank you very much, Damien. It's a great talk. And we do have a question before you go. So Saidiraj Amuru is asking, is the size of chunks based on application type being used? Same chunk may not be same, and it may impact QE.
On application type, so I'm not sure to understand the question, because here really the application is obviously to stream video. So is the size of the chunk variable? It typically is, but not so much about based on the content, but rather because of the structure of the video. Video, you tend to start, well, you always start a segment with a full picture, right? So that you can start with something, and then you work more on deltas, what is moving in the picture. So the first chunk tends to be bigger than the others, the ones after. So again, you know, in my illustration, I was being very high level, but typically the first chunk is bigger. Can the chunk be lower than 1500 bytes? Yes. You know, basically you can decide on the size of the chunk you want. Will it reduce efficiency? Yeah, there can be a limitation on the CDN, but they're pretty low in my experience. How close could streaming video with CMAP get to RTC levels of latency? So it's you're probably not gonna get the level of RTC because in video it's not really the point, right? What we want to do is to find a good balance between the efficiency, the quality of your video, the security, the safety net that you're putting in the delivery of your segments, because you really want latency is kind of an issue, but having frequent rebuffering is much worse, right? In terms, there are many studies that are showing that, and we know that empirically, it's really annoying when it stops all the time, right? So we're not trying to be like sub-second latency, the kind of thing that you can have when you're using more real-time applications such as conferencing or this kind of stuff, but you don't want to be the one lagging behind, right? Is the actual IP multicast used for video transports with multicast ABR? So I'm not sure to understand the question, but multicast ABR, you know, indeed makes use of IP multicast delivery, right? Hence the name. Getting into the details of that technology would take probably too much time, but really the principle here is that you're taking your segment, which is an HTTP packet, right, basically, and you wrap it up in a UDP datagram, right? And when it's UDP, then you can send it through the network, like, you know, any kind of IP multicast. There's no real difference between using I mean, from the network standpoint, whether it's multicast ABR or any kind of UDP that is sent in multicast is the same, right? So there's not much difference. So I hope this answered the question. You know, just don't hesitate to give me a hint if that's not the case in the Q&A.
All right, thank you very much, Damien. I think we'll with that we'll wrap up today's session. We will start again same time tomorrow, and Jason Livinggood from Comcast is kicking us off tomorrow with a talk about the L4S field trials that they have been running over the last few months. So I know I'm looking forward to that, and I hope you are as well. And see you tomorrow.
Bye.
Bye-bye, everyone.